Thank you for your patience. Your event will begin soon.
Yes, okay. I'm going to go ahead and kick things off here. So thank you very much for making it to our Bay Area Iceberg Meetup. I want to thank our hosts, AWS, Databricks, PuppyGraph, Snowflake. I think that's the full set. They did a lot of work to get everyone here and organize this and to stream it across the internet. So welcome, everyone. So to get started, just to introduce myself, my name is Dan Weeks. And I am one of the original co-creators of Apache Iceberg at Netflix. And my career has largely followed Iceberg pretty closely. So at Netflix, I ran the big data compute team, where we oversaw all of the compute infrastructure for Netflix and storage infrastructure. And that was a combination of technologies over a span of time, including, Hive, Pig, Spark, Trino, and a number of other projects. And then on the storage side, everything from Parquet to Avro and eventually Iceberg. From there, I left and I co-founded Tabular, where we built out a platform around Iceberg, and I led engineering there. Recently joined Databricks, and within Databricks, I work in the Open Lakehouse team on storage and formats. So to get things started, I thought I'd ask, what is Iceberg? Everybody seemed to have made it here today, so you probably have at least some idea of what that means. But it's kind of evolved from the very beginning, and you may not know exactly how to frame what Iceberg is when talking to other people. If we go to the website, it says Iceberg is a high-performance format for huge analytic tables. And there's kind of a lot packed in there, tables, analytics, format, but I still get a lot of questions about what is this? Why is this necessary? I've got Parquet files in a directory. Like, isn't this fine? Why can't we just, use the file system to represent the data that we want to work with? Why do we need table formats? To understand this, we need to step back a little bit, and maybe a little too far, we'll talk about where this all started. And when I think about this, it all really started around like the early 2000s, mid 2000s, where we kind of got into the situation where distributed systems and data started to intersect. Distributed processing existed before that, data processing existed before that, but this was a time at which there was a rapid growth of a certain set of capabilities, including cheap storage that's really high density, high-speed networking, and commoditized compute that all kind of came together at the same time. And this is where we got the papers around distributed file systems, patterns for doing distributed processing like MapReduce. And at that time, there were a lot of engineers working on this, myself included. And we looked at this as an engineering challenge. Like, we approached this as a question of like, how do we scale? How do we make it faster? How do we make it more efficient? And we did a really good job at that. At the time, like, we were all competing on like word counts and sorting data sets and indexing and Netflix recommendations, all of these kind of challenges. And that's fair. It was a really interesting time. There was a lot of work that was going into this. But the problem that we ran into is that we outgrew our ability to provide guarantees while we were doing that processing. We could process a whole lot of data, but you couldn't necessarily guarantee that it was correct or that it was complete. And at Netflix, we really ran into these challenges because we were building out one of the first cloud-based platforms. And this kind of really put a lot of focus on some of the areas where performance and scalability were challenges in that processing paradigm. So for example, like listing performance is, 100x what it is in HDFS or something like that, at least in the early days of the cloud. Partitioning data and how you structure it was painful because you'd have to rewrite it if you did it wrong. Pruning became a major problem because going and touching lots of files at low latency created a really slow experience for users that were trying to perform ad hoc operations. Metastores didn't scale. That was a point at which like our metadata started becoming big data, and it wasn't something that we could really pull together in a single system and rely on. It just didn't scale. And then there's all the guarantees that we didn't have. Atomic operations, being able to selectively update tables, even like appends or commits. And the cloud kind of made this even harder because the file system concepts that this was built on didn't exist in the cloud at the time. And then lastly, there's like data set consistency. And this is a big problem because you could just like throw files in a directory and now it's magically part of your data set. Or you have a directory that's under there and some engines will process it, some won't. So you'll get inconsistent results. And the worst thing for users was the usability was really poor. Coming from other systems that did analytics, they had lots of strong guarantees and they assumed that they could do those same things here. Schema evolution, having data types that are consistent, schema on read was a big problem here because it would kind of try its best to interpret the data for you. And you might get different results depending on what you're using to read it. And then the last thing is a lot of the functionality that was available to people was directly reflective of the file formats. You can't reorder columns in a CSV file. Maybe name projection or index-based projection is used by your engine and you'll get different results. So at Netflix, we actually spent a number of years trying to solve these problems, and we approached each one kind of individually. We tried to, parallelize and provide easy restatement of data, re-implement the metastore, and a bunch of the functionality about like file system operations and how things interact with the cloud storage. We tried to improve the guarantees. We created things like the S3 committer to try and atomically, commit data to the data sets. We created complicated protocols within the metastore in order to like swap partitions around and try to provide some semblance of guarantees. We even created consistency trackers that were tracking indexes in our storage system to try and ensure that they actually are consistent. And then the last piece was, from the usability perspective, we just stopped letting users do things. We restricted certain behaviors. Some of them we couldn't, and you just, learn where the sharp edges are, and they kind of develop a sense of learned helplessness. You just don't do things because you're not sure if it's going to be okay. So at that point, we were actually back in around 2017. We were in a situation where we were trying to rebase our platform on a newer version of Spark. I think it was like a major release version. And we were looking at all of these changes that we had made across all of our infrastructure to how we read files, how we handle, operations. And it was really daunting because we knew we had to re-implement this on an entirely new version. A lot of stuff had changed. And we were frustrated because you look at this and we say, this is what my life is going to be like for the next 10 years. I'm going to be rebasing these changes and constantly fighting these problems. And it was at that point that Ryan Blue and I sat down and we were like, well, we can either do this or we can go back and we can say, let's redesign this based on fundamentals. Like we had lots of conversations prior to that about how we would build, tables if we could do that from the ground up. And at that point, we made a pivotal decision to go ahead and move forward with this. It wasn't an easy decision. We got a lot of pushback even from our partner teams because it means a lot of change within the ecosystem and a lot of rethinking about how we solve problems. So we're back to the question, what is Iceberg? So if I were going to talk to people today about what Iceberg is, I'd break it down into kind of 3 different categories. The first thing is specifications. You hear a lot about the Iceberg table spec. It's not the only one. We actually have a REST specification, view specifications, encryption specs, and I think that there may be 1 or 2 others that I can't think of offhand. The specifications really define how we lay out data, and that's the table spec. And once everybody can kind of agree on how we lay out data, anybody can read it. And that's really great. That took us a long way. But then we found that the real problem was getting access to that data. How do you interact with it? How do I look it up? How do I mutate it? And that's where the REST specification came in. And the combination of these 2 things is really powerful because it means that anybody who knows how to speak the protocols and understands how to read and write the specs can touch data wherever it is. You don't need to go load it into systems. You don't need to move it around. It's a really powerful concept. The next category is reference implementations. In order to validate the spec and provide examples of like how to actually do the things that we define in the spec, we have libraries, APIs, and integrations that we provide. This is really helpful because it means that anybody who wants to use these libraries can actually just abstract or rely on them to solve some of the complicated problems that we do in terms of like managing metadata and how do we process the data files. Of course, you can implement the spec directly too. There's nothing wrong with that. But this is an easy way to integrate this into other systems. And then lastly, we have the cloud and storage implementations. These are easy ways to just connect to the common providers, AWS, being able to interact with both the storage and the services in that ecosystem. And the last thing, and probably the most important, is the community. That's how we actually got here. When we talk about community, the largest group is actually our users. There's so many people, all of you, many people out there who are just using Iceberg to solve problems. And that's great. We really value that. We like the feedback from the users. We want them to be part of the community and contribute. The next thing is the contributors. These are the people who are spending their time contributing code, providing reviews, arguing with people both on mailing lists and in syncs and things like that. But we really value that because it results in a better product that solves more people's problems. Then there's a large community of the OSS projects around this. Apache projects, non-Apache projects. We've talked about a few of them. We'll probably talk about a few more. But this larger community is all centered around trying to work together in terms of reading, writing, interpreting, processing, doing the things with data that we need to do to extract value out of it. And the last thing is vendors. Vendors are the ones who actually pay salaries for a lot of us that contribute to these projects. They get value out of it too, but they're a major component of both like the Apache Foundation as well as Iceberg. So talking quickly about the specifications, the specifications are really nice because it brought everybody together in terms of having a consistent language to talk about data. Data types, metadata structure, guarantees that we provide. And then lastly, especially with the REST specification, standards that we're drawing on other areas of the community for authorization and specifying the actual protocols themselves. The reference implementations have grown quite a bit too. Initially, it was just the Java ecosystem, which is largely, derivative of the Hadoop ecosystem and lots of the tools that existed there. But it's expanded quickly. Like Python is probably nearly getting as complete as Java in terms of being able to interact with the data and metadata. It's great for people who are doing data science and don't want to work with big processing engines or something like that. The Rust and the Go ecosystems are growing very rapidly. So this expansion has been incredible. And we really value all the contributions and the various projects around that. Then there's a wide range of OSS projects. These ones are largely the ones that we have in the actual Iceberg code base that we're working with or we provide connectors to, but there are so many more. I gave a presentation a year or so ago, and I think I had a dozen open source projects, a dozen vendor products, and I missed probably a dozen more. So it's really expanding in terms of just the ecosystem. And the most important thing is a lot of this focus is about interoperability, which is where catalogs, storage integrations, common functionality all comes together. The last thing I'll touch on is community. We are an Apache Software Foundation community, and some of the goals that we have are really to be neutral and inclusive. We've got lots of people of different backgrounds, different companies, all contributing and working together. We want people to be open and transparent. Share your challenges, why you want to make changes, come to the community with good intent. And the last thing, and particularly with the Iceberg project, is we lean very heavily into discussion and consensus. We don't like to move forward unless everybody is in agreement, or at least willing to move forward. That doesn't mean that we don't argue. We argue a ton. There's a running joke about me and Ryan arguing. So that isn't necessarily a bad thing. We think it results in better outcomes, but the reality is we want the entire community to be working together and moving forward together. So where are we now? Well, the current state is, if we're looking at the actual table specification, the version 1 and version 2 are actually pretty well adopted. We've got multiple language support. We've got a lot of engines that know how to use the vast majority of the capabilities in those areas. You can see the list of things. You're probably familiar with many of these. The V3 format is something that's been ongoing for a while now, and it's quickly coming to convergence. A lot of the things that we want to include in V3 are really coming together. Many of the specifications have been drawn up and are in some process of being adopted or in review. And lastly, the implementations are going out. Many of them, deletion vectors, there's a talk later on about that. We already have the implementations in, so we're working on formalizing those. So what's in V3? V3 includes a number of exciting things. First of all, data types. Variant data type for all those people who like semi-structured or slightly unstructured data, especially JSON. This is so much better. It also includes shredding, optimizations that engines can perform to be super fast. The geotypes, we're working with the Parquet or GeoParquet community and Parquet community to settle on those. Timestamp nanos and unknown, throw it in there because we didn't have it. All of these are actually community efforts. There's a lot of collaboration that's going on between the Parquet community, the Delta community, the Spark community, many of these other communities that have actually built out these data types. And a big part of this is making sure that we have consistency in terms of how we represent data, because the last thing anybody wants to do is go and restate a bunch of data just because you had a small type incompatibility. The next thing is improved deletes. There's a big talk on it. I highly recommend you listen to it. But it is about improvements that we made over the previous positional deletes, how we represent them, how we track them. A lot of improvement there that we think will really help with merge and selective delete capabilities. The last thing is row lineage. Adding row lineage allows for doing row tracking, incremental processing, and there's a lot of patterns around CDC and things like that that can build off of this functionality. So on the REST spec side, there's been a large amount of adoption over the course of the last 6 months to a year. A lot of people are coming out and they're recognizing that this is a great way to make data accessible, to standardize on how you interact with data. It doesn't mean necessarily that it's optimized or anything like that. There's always space for that in tools, and we want to encourage that, but being able to access data and mutate it in a standard way is incredibly useful. So these capabilities have largely been adopted. There are many providers out there, both vendors and OSS projects implementing these capabilities. And what we're looking right now is how do we improve this? A good example is server-side scan planning, pushing some of that complexity of working with the Iceberg metadata back to a catalog or service. This really helps the client because it needs to be less complicated. And there are a lot of situations where you really just need to know which files do I need to process, instead of the fine-grained details of how to work with the metadata. Fine-grained commits is the other side of that. If you need to be able to append to a table or add data with all the guarantees, but without all the complexity, that brings that to the table. And then we have been tracking multi-table transactions for a really long time. I'm really excited about this, and I think we're starting to get to a point where some of the technologies around this and the kind of guarantees that we want to specify for these behaviors are getting to a point that we can actually round this out. And then there's optimizations like freshness checking, things that will help engines in order to better perform against a REST catalog. So then where are we going? I would say that Iceberg is a community, so nobody can specifically say what the roadmap is, but there are a lot of things that are going on. And I would say the way that I would talk about it is to kind of distill what kind of problems are we seeing from the community? What are people running into? You may have run into some of these. So one is around scalability and performance, the metadata size. There are lots of things that you can do that will actually blow up your metadata in bad ways. And we want to make sure that there are easy ways to curtail the size of the metadata, make that really efficient, and make sure that it's performant for the use cases. The next thing is scan planning. We want to improve scan planning. There is definitely a lot of overhead in that, and when you get to really large data sets, that can easily become a problem. Fast commits, we've seen, especially in streaming cases, that people want to commit to tables really, really fast, on the order of seconds. And this exacerbates some of the problems around metadata size and scan planning, and we want to start looking at ways to solve those problems. And finally, catalog optimizations. There's lots of things that we can do to make those better. The guarantees that we want to bring, we ran into actually as we were working on the V3 spec, being able to do type widening. There are certain limitations that we have in the metadata structure that actually make that quite hard. And we had initially planned to do some work in that area, but the nuances and some of the checks that we have to do and the uncertainty about how we would actually represent that was enough to kind of push that back and say, hey, we actually need a more fundamental rethink of that area to make sure that we can provide strong guarantees there. Partition stats is something that's been worked on as well. Again, optimizations, improve query performance. And then there's a wide range of maintenance types of activities because a big part of Iceberg is deferring work. We want to be able to make commits, reads as fast as possible, but there is a maintenance component. And what people run into frequently is cases where something has been deleted because of either bucket retention or something else, and they need to be able to restore tables to a healthy state. There are also cases where you can actually recover data in safe ways. And then finally, more advanced metadata management for things that are ready to be removed from the table and is just accumulating over time. Next thing I would say is actually a challenge around scaling the community. We started off as a very small project, and we've grown very rapidly. And in order to have a really healthy community, we need to make sure that we are communicating well, we are talking with others, we are helping other people solve problems, and we're collaborating with good intent. And this is something that we've actually seen a lot of successful activity on, especially in Slack. It was originally just a few people trying to answer everybody's questions, but now you go in and you see people talking to each other, how they solved problems. It's really become an incredible community. Okay, well, how do you get involved? It's an Apache project, and there are kind of standard ways to engage with the Apache project. One, of course, is like we do a lot of collaboration on Slack. So if you're just like asking a question, you want pointers to something, Slack is a great resource. I think we maybe are over 7,000.
Just checking. 6976.
6976. Go join Slack. Push us over. Push us over the fact check right there. The next is the dev list. This is where all the real work gets done. Anything official needs to happen through the dev list. This is where we do votes, where we do discussions, participate. It's a great thing to sign up for because you actually just get a nice little thread of what's going on in the community. And then the last thing is contributing. GitHub, you can open pull requests, add docs, create issues. We love to operate through that mechanism, and we actually watch that carefully. Lots of people are looking at it, issues that are coming in. So please join the community, join us. Thank you. I don't know if we're taking questions.
Thank you, Daniel. Really appreciate it. Open for questions. We do have some time. Very hard to get Daniel sometimes, so I think this is a great opportunity. I really want to thank you. The more I hear, the more and even today, we haven't even scratched the surface. This is how, this looks so, such a beautiful problem. And it's not us coming in and saying that when we work with customers, real world problems out there. And variant data you talked about, these are problems that are real world problems. And I think what you started out, and that's become where the community has really contributed to. So really thank you to everybody, first of all. Thank you. Please, let's take questions.
I think we have one over here.
Great without a question.
Hey, thanks, Dan. Really inspiring talk, and really glad to see you. So I found it interesting you mentioned about how in Netflix you initially were having other solutions, then you decided to start over from the fundamentals. But I'm wondering what helped the most for you to convince all the stakeholders and the leaders in the company to take such drastic change?
We got some stakeholders right here that could probably answer. But it was definitely like some of the earliest use cases were the people that had the most pain, right? Whether it was a scalability challenge, they had huge data sets that they weren't able to work with. Their users weren't able to actually query that data. For example, there's one that's one data set that's like a telemetry data set of like all the metrics that Netflix collects for everything. And they were very limited. The data scientists were very limited in how much data they could actually consume. And a lot of that really had to do with one of the problems of just like how you partition the data and how selective the actual planning process is. And the listing performance and trying to just enumerate which files need to be touched and touch them just to find out that you don't even need to process it, that could take 15, 20 minutes. There were cases where it wouldn't even complete that process and they just had to start over with smaller data ranges. And Iceberg actually brought that down significantly. We did some early talks on this. I think it got it down to just like minutes, like single digit minutes to process across multi-petabyte warehouses or data sets, single tables. So we attacked the people with the pain first, and they were willing participants. But then there's, of course, like this long tail. And that's a challenging problem because you go to people and you say, hey, I want you to switch over to this new format. And they say, I get the same result. Like, I'm not doing anything. I haven't touched it in 2 years. Why would I change? And so it's really about making sure that you provide enough of a carrot, like the functionality, the capability, and they see the value in moving over. So it took a long time. It took many, many years to convert the warehouse over to Iceberg.
Yeah, thank you so much. And I saw that when you were sharing version 3 specification, and there was an update on timestamp, right? My question is that will this timestamp will include time zone information in it, or it will be without time zone?
So it's both timestamp with time zone and timestamp without. They're all represented as UTC. So the one thing that you need to know about the timestamp, and it has been a little contentious, is like we're actually storing it as 64-bit. So that really limits the range of dates that you can use. And this is kind of a reasonable trade-off that we're trying to make between like where you actually need nanosecond. You know, if you're doing geological events back in, you know, however many thousands of years ago, you probably don't need nanosecond precision. So it's kind of a compromise in terms of like how we can represent it versus what the utility is of a timestamp nano.
Okay, because just a small follow-up question, because current version of timestamp with 6 nanosecond, like microseconds, is only with either local time zone or no time zone. It does not include the actual time zone. Is that correct understanding?
Yeah, you don't store the actual time zone with the data.
I just have one question. This is about the REST catalog. I didn't see anything in the community things that you listed out. Is it pushed for V4 or what is the?
Oh, I did have a slide. It was not, there's no like specific version of the REST catalog. It's actually just kind of like a continuously moving specification. We try and make sure that it's both forward and back, or well, at least backward compatible. So there were a number of enhancements that I did list for the REST specification, but it's not like a strict version increment. So we'll kind of like add those incrementally.
Yes.
Hey, so when you talked about fine-grained commits in the future, so how fine-grained will this commit? Like, will they be like record level fine-grained or what?
It's still an early discussion. I think the most obvious things are appends, right? Because there are a lot of systems that may be able to like produce files and want to quickly append that to a table. And they may not have the logic to perform the commit, or they may actually want to defer the commit. So if you're just like streaming files super fast, you may actually want to accumulate them up for some amount of time before you actually perform a commit. So these are all just different ideas that have been thrown out. Nothing has actually been settled for the fine-grained.
So is it mostly driven by streaming ingestion, the fine-grained commits?
I think it's a combination of streaming and trying to incorporate clients that don't have as much integration with Iceberg, that don't understand the full metadata or don't want to be able to produce the full metadata. But streaming is a major component in that.
My question is on the V3 spec. Is there a timeline when it will be out? And second follow-up is, which topics in the V3 spec are already agreed upon in the community and which are still being debated?
So there are a number of things that have already been agreed upon and voted on. They've been introduced in the actual spec, so you can go read those, and they're annotated as being part of V3. When it'll actually close is really up to the community. You know, there's a drive to complete some of the work that's already been defined for V3. And then, you know, of course, we need to go through the process of actually voting on those things and making sure that we have proper reference implementations. I think right now, Parquet has the variant spec that we're leveraging from Iceberg, and that isn't fully finalized in Parquet. So we're kind of working with them to finalize the specification in Parquet, get reference implementations out so that Parquet can close on that implementation, and then Iceberg will be able to close on the actual Iceberg variant implementation. We're working with those
I have one
communities.
question.
Yeah.
So now that LLMs can search and summarize data from various sources, how will Iceberg make things easier for LLMs? Do you have any kind of reference implementation around that?
I do not. I work on storage and table formats, which are very important to AI, but I am definitely not an expert in AI. So I couldn't hazard to guess what that would be.
We have time for one more question. One more here. CDC. When we're gonna have a standard Iceberg CDC?
That's a good question.
Of course.
Like, I mean, I think that there are a lot of primitives that are coming, like the row lineage is an important one, the incremental scans, things like that. And, you know, there's work that's being done to help in like Spark, introduce interfaces for DSV2 to help abstract some of those things and standardize at least the implementation on that side. But I think that there's still a lot of work going on in CDC. It's still kind of coalescing. So
So not in V3, right?
not something specifically CDC that I'm aware of. I
Okay.
haven't heard anything. Like some of the constructs that you'll need to build good implementations on top of it will be part of that, like row lineage.
Thank you.
Okay. I think we're out of time, but you can catch me afterward.
Yeah.
I'll be hanging around.
I would request, because we are about 15 minutes behind, what I would, if you're around, please, if we can also ask a few questions to you, maybe outside or maybe, that would be awesome. But I really appreciate it. Thank you, Danny.
Thank you. Thank you, everyone.
First of all, my name is Tej with AWS, actually over here. So those of you who are traveling far, welcome. I know Lakekeeper team has really come from Germany, so I really appreciate the distance you all are traveling. Really appreciate you taking the time from your day to be here as well. And for the teams that have actually helped organize. I do want to give a shout out to Zenny and team from PuppyGraph for organizing a phenomenal dinner, by the way. So Happy New Year. When we were discussing, we wanted to make sure that there's something for everybody, and the number of menu items is about 35 at this point. So I think everybody will take away something from here, including food. But I really appreciate, and we have a really good lineup. We had call from Starbus who actually couldn't make it, but I really, we'll try to get him back at some point. But I think to keep this going, we wanted to kind of skip the session up a little bit and have PuppyGraph actually come on stage. Denfeng is the CTO and co-founder of PuppyGraph. He is data and data processing extraordinaire. So if you look through what he's done and what he's accomplished, I was really amazed. So I'm really happy that you're here. I think you're going to talk a little bit about log processing, right? So, okay, please take it away. Thank you very much.
Check.
You can, where do you present?
Either side. That one. Yeah, the slides available on the screen.
Slides are actually in my laptop. The laptop is in the other room.
Okay.
Do you have your laptop here, or
I should have my phone.
let me quickly go. I don't know if anybody has any questions, so he's right here. But let me go grab the laptop and then we can talk.
right, I'll start. Hi, everyone. Thanks for coming to this meetup, and it's fantastic. This is Denfin from Puppygraph, and Puppygraph you see from my jacket, from the logo, it's something about a graph, right? You can also see from the front page. Not many people know. Sure. Not check. Is this better? Check. Okay. Not many people know that actually Iceberg is one thing that actually inspires us to start a startup. And we are a startup focusing on graph query engines on top of different data sources. And we're going to cover that, probably later. Today, we're going to talk about from logs to insights. And there's agenda. Before that, I've, talk about myself and CTO, co-founder of startup Puppygraph. So the agenda today is consists of two parts. The first part is how we're going to do the step-by-step thing from logs and building that as a graph or using graph to view them, and then providing cybersecurity insights from the logs. Second part, which is more interesting and that matches our idea of when we want to start this company, is how Iceberg makes everything sustainable and feasible, and making sure we can provide scalable cybersecurity insights as well as other scalable analytical insights from the data. So let's talk about logs first. Logs, right? Logs are everywhere. That's data entries, recording some kind of events, some kind of actions. So on the right side of the page, there's firewall log, this one entry. It's pretty standard logs, date, has some IP address associated, and some protocol, and pretty interesting. There's action, allowed, and the policy says okay, because we allow HTTP traffic, so we just allow that. This is just one entry emitted by a firewall. So let's take a look at this logs, right, in more depth. So first, it has some properties, and that's useful for analytical use cases, like when we actually look back, let's say, after a month, and we want to figure out what happened during that time, and we want to just take a look at the actual action that was created and when that was happening and why the firewall thought, okay, it should be good to just allow the traffic, right? There's reason that action. The other part is also interesting. That is, oh, it has a source IP and a destination IP address associated with events. That inspires us to say, okay, events, right, or log events are associated with entities. Here we say source IP is one entity and destination IP is another entity. So that actually, why don't we just take a different view on the same line of the data? So we move on and say logs can be viewed as graphs because they are associated with entities, and we can just use a graph to view them. So we only presented one line of log in the previous page. So let's try to just build them as a very simple graph, right? It's single edge graph, and we have entities. Now we just model them nodes in the graph. On this graph, we have two nodes, each of them representing an IP address. And the previous log line is also describing an action or event. We want to actually model them as a relationship or edge between these two entities. And what is more interesting is this is more like a labeled property graph because the edges and the nodes can have properties. In the previous line, we talked about actions, right? This visits is allowed, and there's also reason. Oh, this is TOS traffic, so everything looks fine. Timestamp, which is pretty important for any kind of data analysis. So these kind of properties will be also modeled as properties of the related nodes and edges. So that's pretty cool. Just one line of but this is just a very simple version of the graph. Really, there's nothing too much we can do with this one line of data. And let's see what will happen if we have tons of lines. So there are two ways of like getting more data, right? Or like two different directions. One is we'll have more lines. Let's say we have one access log and we'll have like tons of them. Realistically, IP addresses right there, and the firewall is emitting traffics like all the time. The other way is we want to make sure we get more type of data or more type of log into this place. So some examples consist for like, we talked about firewall accesses. There could be other parts like IAM role, association. So on this, there could be some logs like, okay, the machine is associated with some IP address and some IAM role like on this graph, right? Or some logs talking about IAM role D has associated like, policy and like, security policy E. And security policy E actually grants you to access some highly sensitive database. So this is a graph. On this graph, it's modeled from different type of logs. And imagine that you have tons of logs everywhere. It's actually going to be a pretty huge graph that built on top of these logs. Now we have a better graph than what we had in the previous slides. What can we do? So we want to get some security insights, right? Or like, sending some graph queries to it. So one thing we can do is like just do this like cloud security posture management. And this is like just we wrap things, right? Like logs to graph, and now it's actually providing real insights. So let's say we want to see if the database, right? Because we assume that database F here is a highly sensitive one, and we want to make sure that, okay, is it going to be attacked by IP address like 1.2.3.4, which is categorized as external one? This is a query, and the red dot line here is actually representing a query which can be applied on this graph model. The other way of saying that's like, let's say if we have some way of querying this graph, then we should be able to get the answer, whether there exists a way of starting from IP address 1.2.3.4 to this highly sensitive database. And these kind of queries are pretty suitable to like data, query languages, as well as like like graph data models. Another important thing is like data keep changing, because coming back to the logs, right? Logs are emitted every like millisecond, and there'll be so many new changes in the same set of like the data set. What if machine C now associates with like IAM role, which implicitly grants the policy and access eventually to this highly sensitive database? So this kind of change happens locally, maybe in a in a log file of some machines is like on policy change or IAM role association. But if we use a graph view to view this holistically, we see that actually it forms actual path starting from the like upper left corner, the IP address, going down to machine C, going down to IAM role, and eventually to database, which means the query result to the previous query would change as the data changes. And that's totally expected, but the graph here helps exposure some of the like latent insights that can be formed between a long length, like interconnected data. So this is the first part. We actually get some value from modeling the data as a graph and answering security-related questions. Everything looks fantastic. But we talk about logs everywhere, and it's emitting. It's like huge amount of data. So realistically, right, even that we are capable of building something like this, we need to understand how to make the cost feasible. And when we say cost, it's not only about the cost for storing the data, it's also the cost for managing the data. And on top of that, we say, oh, graph query is bringing in some, security insights. How do we make sure the graph query part is also cost efficiency? So how to reduce that, right? How to reduce the cost, how to make the cost sustainable? Well, this is a longer version of the quotes I get from the Iceberg. And what is Iceberg? Iceberg is a high performance format for huge analytic tables, and it brings reliability and simplicity for SQL tables to big data, while making it possible for engines like Spark, Trino, Flink, Presto, Hive, and Impala to safely work with the same tables at the same time. So when we want to find the answers to our previous questions from these slides, right, we see several important points. And thanks Dan for giving like awesome intro to Iceberg. First, it's high performance. High performance means like we can do a lot of things with, we can do more things with the same cost, right? We can handle larger scale of data with huge analytical tables because Iceberg is designed for that. It also brings reliability and simplicity. That's also important because we're going to cover that later, like why it helps with reducing the cost as well. And it talks about engines, and the separation of compute and storage actually helps a lot in reducing the cost. In the end, it's the same idea of like same copy of data in multiple engines that actually brings a simplicity and simplicity and the cost efficiency to the graph analytical world as well. So now we have Iceberg here to help, and we want to see what actually we can do with the graph analytics, and how do we get the previous graph analysis done in a way that is more efficient. So Iceberg provides a way. When we say Iceberg analytics, right, it's like typically Iceberg with engine, like different engines that we've seen in the previous slides, and we're going to learn more in today's Meetup as well. So if we apply the same philosophy to graph analytics, it's going to be Iceberg plus graph engine. And that's exactly, one of the inspiration for us to start this project and company. So I'm just presenting an example architecture here, assuming we're talking about CSPM, which is cloud security posture management, right? We'll build application on top of that. The logs data storing Iceberg, and there will be different query engines querying the log data, providing different type of insights, and they expose different type of querying language or programming interface or other type of APIs to interact with the application. So this is like a multi-layer architecture. But one interesting thing is it has multiple multiple type of engines, multiple types of query language, but it's a single copy of data. So because of we actually leverage this Iceberg thing, we think this is considered as a scalable architecture, which is capable of providing analytics in a cost-efficient way. So I'm just putting the graph part on the right side, right? There's Gremlin and Cypher, popular query languages for graph, and there's graph query engine on top of Iceberg. Let's take a look at what actually it brings, right? Let's do analysis, and this is the second part of the, how once we have the Iceberg, what exactly cost is being saved. So we break it down into three parts: data storage, data management, and graph query cost. So data storage, first, Iceberg, right? Iceberg is designed to be storing huge amount of data, and we talked about, and we were scared about, okay, Iceberg, let's say log data increasing over time, and how do you make sure they are efficient, stored? I think one architecture adopt here is Iceberg actually allows you to use object store to store data that is keep growing all the time. And object store is considered to be pretty scalable. And you can also choose different performance tiers based on your use case. If you're looking for more stale data, right? You want to do some batch analysis. You don't really need that super fast IO or high latency. Then you can choose more cost-efficient storage layers. But if you're looking for something like is more real-time, then you can actually choose like highly optimized storage for high latency, for low latency. The other part is compression, like for example, Pocket file, right? That comes with like different compression algorithms that allows you to optimize for first, right? Data size are growing, so we want to, do some compression to make sure the storage is compressed, and compression also helps with data transition that actually impacts like query performance, because when you actually run query on top of this copy of data, there are lots of things can be done with the same amount of time the data are compressed. The second part is data management cost, right? So this is in many cases to be actually ignored because we talk about separation between storage and compute, separation of storage compute, but management is actually like huge amount portion of that when you actually take a look at the whole cost. One thing that is like really fantastic is about Iceberg's like the REST catalog protocol, which brings a spec centralized way of defining how the engines can interact with the data and the data management metadata. And this actually simplifies lots of like dev and management cost, and making sure the data that you have today can keep evolving, and it's also designed for future, because if engines are designed to contact the data in the spec in a way that will be keep evolving, then your data will be available to be queried in a way that is like not only ready for today, but also ready for future. And catalog also provides a lot of like, feasible like features like multi-layer namespaces. And because of the separation of storage and compute, the data changing part is actually handled by storage. And Iceberg comes with the like asset management, which allows data, to be committed. And I'm super excited to see like in future versions, right, there'll be like more fine grain like commits. I think that's going to be like super helpful for lots of use cases. And a single copy of data is also critical because in a different paradigm, when you want to create different queries, query paradigms, or like different query patterns, a typical use case is like you just create different databases, and each of them will persist some part of the data, and maybe having a full copy of the data. With the Iceberg, right, this architecture, you have same copy of data, different engines on top of that. It's already saving the money. It's already saving the cost because you don't have to have the data replication. It's not only having another copy of the data will be costing some of the amount of money, also the cost of not having to maintain the complex ETL between different copies of data and different data sources is a huge win for this kind of architecture that you have multiple engines on top of the same data. So the last part is how do we actually leverage Iceberg to reduce the cost for graph queries? So one thing that is critical for analytical compute use cases is a columnar format or columnar file format. This is actually important for lots of analytical data use cases, but it's also critical for graph actually. Because if you think about graph, right, we talked about graph, they have nodes and edges. So we didn't touch the details of implementation, but you can imagine some of them will be part of like a metadata, like this node connects to the other one. And some of them will be just the properties, right? But when doing the matching or doing some kind of like, graph-based path finding, all these kind of like graph queries, many of the fields will be there, will be useful for some of the queries, but not all the queries. And columnar storage format allows you to fetch the necessary columns only for the query that you're running. And this is actually like a pretty critical change from the role-based like a graph analytics. And columnar format also improves the efficiency of the compression And we talked about compression in the previous slide, right? Like it's important for data like storage saving. And we also see that columnar format allows vectorization compute much easier, because if you think about vectorization compute, it's like multiple multiple elements with the same type, right? They'll be treated as a vector and do the compute with some vectorized instrument. So these kind of things accelerate the compute. And because compute is more efficient, with the same cost, you can do more. And data skipping is another important feature for graph analytics, because in, like data have metadata, and in many ways where you want to find the association between edges and nodes. And icebergs like, min max stats, as well as Lagoon filter and other index-based filters allow it to get the associated files or blocks in an efficient way without reading all of the data. And many of the data actually can be inferred from the metadata without reading any of the data sets. And last, single copy data actually allows engine collaboration. And this is also another way of saving the query cost, because you can pick up the best query for the best use case. And you don't have to do everything in the graph. You don't have to, like some of the queries are actually more feasible in other type of query engines. But having this type of architecture allows it to be queried in a very efficient way and most suitable for your use cases. And that's basically is like what inspires us to start a company, and super excited to share about this. And I think let's just like summarize it, right? We start with logs, and now you have Iceberg plus Graph Query Engine allows you to provide scalable analytical graph insights, including those for like the example we show in this talk, cloud security posture management. And it can be applied to more use cases as well. And that's it about today's like talk. And any questions? Thanks.
Thank you very much. Open for questions. Hard ones, no easy ones. You have easy one or hard one?
Hey, when you mentioned about the single copy of the data, like so let's say Iceberg, I think the way that, and based on my limited understanding, has its origins on the tabular data, right? Like tables and table 2, and they are all connected by keys. Then on the top, we have a graph layer, which is all talking in terms of cipher query or language. So now it means like, does a cipher query translate it back into some sort of SQL layer or the table joins, and then goes back to Iceberg? Is it how it operates?
So yeah, let me repeat the question. I think the question is like single copy of data, and they are living in tables. And for graph queries, like are they actually getting back to some of the like table reading and then doing the join, right? Is that the question? For like, so Cypher is one of the popular like query language for graphs, and it's different from if you see a syntax, right? It's not like okay, reading from this table. So we took like this as in a way that lots of parts are similar when we want to do the joins between tables and we want to do the graph queries. But there are some fundamental difference where some of the strategy are more suitable for graph. So the way we took is actually to read the tables as for like, leveraging icebergs. I think there's like, scanning technology to allow you to skip more data. But once the data are pulled back, you're going to run that in a, in our own engine instead of like directly running that as like a Spark or like Spark SQL. So the data fetching part, that's why like we are talking about single copy of data. They are stored as tables. So even in our architecture, we actually getting more about like like metadata environment and like data like storage environment, right? All these kind of like gains on the non-graph side is actually beneficial for graph analytics as well. So ultimately, it's just analytical use cases. And I'm not sure if that answers your question.
I was thinking like, I was trying to visualize the notions is different, right? Because in graph, we do a traversal, as opposed to like queries, it's like iterative join, like table 1, table 2, table 10, and goes to the depth. So that's what I was trying to do.
Yeah. We actually write some implement some of the protocols, like query protocols. And once the query protocols are basically think of parsers for graph specific query language like Cypher and Gremlin. And once those protocols, they have the parser, then parse a query language into some logic plan. And logic plan will be actually converted into physical execution plan. And in physical execution plan, they will be actually reading the tables, leveraging Iceberg libraries.
Very nice. Thank
Yeah,
you.
hi.
One more question. Oh, you have, yes,
Oh,
please,
yeah.
please go ahead.
Go ahead.
Yeah, hi. Thanks. It was a great talk. So the question I have is about your query engine. Is it like an open source query engine you have picked up, or it's in-house developed proprietary development for the graph query engine?
Yeah, so right now we actually don't open source, but we have like a free Docker that is available for downloading. We open source part of our system, like part of like the Cypher, I think, related, and also the visualization part. But right now, the development of the core engine part is not open source yet.
Hi. So are you building indexes that are stored outside of the data lake to actually make a lot of these calculations feasible, or is it everything just directly on the lake in the Parquet files managed by Iceberg?
I'm not sure if I understand the question. Let me try to repeat that and let me know if that. So your question is like, are we building something that's like able to connect to different data sources, or is purely on data lake? Is that it?
Not quite. Are you building like indexes to do the graph calculations sitting next to the data lake, or does everything just always read the cold data to resolve your queries?
I see, yeah. So the question is around, let's say if we are querying the data on Iceberg, right? Is that like we are leveraging only what Iceberg data provides, or are we building extra indexes? Yes, we are. But for that, we leverage a lot of like from Iceberg, like for example, we talked about the data skipping part and all this like min-max thing. And imagine like you can also organize the data in a way that is more suitable for graph cases, if your main use cases for graph, like you can sort them by some of the IDs. And in this way, Iceberg data can actually help you, right? Like the data skipping, like the index, right? All the things are already there in place. And then we build extra indexes for to suit other type of graph queries on top of like maybe non-Iceberg, but on our like local disk as well.
Makes sense. Thank you.
Yeah.
We have one more question. Last one,
Yes.
I think.
Give some insight into what kind of graph queries the customers are using.
Could you read that? Sorry.
Insight into the kind of graph queries customers use PuppyGraph for, like what applications they're using it for.
What application you mean? What industry or like what use case?
Yeah, I mean applications and what kind of graph queries, like reachability queries.
Oh, I see. Yeah, I think I didn't put any of the queries in my slides. Some of the query will be like, so they're like, popular query languages like Cypher and Gremlin. They have, I think they're the different, one way of saying Cypher is like more similar to a descriptional, like query language, where you describe, you want to do some pattern matching. Let's just use this as example. So let's say this is a data and this is a graph, and I want to check if there's a path from some node to another node. And sometimes I want to do this kind of pattern matching to scan if there's any matching pattern. So instead of saying, is there path from 1, 2, 3, 4? I would probably just say, is there a path from any type of IP addresses or anything to a database? So using Cypher and Gremlin, you can actually describe this as a query. It's just similar to in SQL, you would see, okay, select everything from this table and join, right? So you write the Cypher queries, and the the response would be matched data, also, I think, serialized in a pathway so that you know the structure and the relationship between elements returned, you can directly apply them in further analysis and computation as well. Yeah, but we can catch up and share more like about the graph querying things as well.
All right, perfect. Thank you again. Really appreciate it.
Thank you, and thanks for the.
Thank you. All right, this is very exciting. A quick announcement. April 8th and 9th, Iceberg Summit is coming to San Francisco. So please, call for papers and sessions is open. Please do, submit your abstracts. And please I plan to be here as well. I think it's going to be phenomenal. We're spending a lot of time trying to understand and figure out where the community is moving and how we want to, kind of organize it as well. So it gives you the best benefit. So April 8th is live and April 9th is going to be live streaming. So you will have more options and we'll be able to reach a lot more people as well. So that being said, let's take a quick 35 minute break. And we come back with a fireside chat. Denny, you're going to be leading the show with Jason, and it's going to be phenomenal. We're going to go behind the scenes. So get your coffee, get wired up, and grab some. There's boba tea, or there's tea over there. It's very exciting. So please go try that, and come back. Thank you.
We will be back shortly. Enjoy the background music as you wait for your event to return. Your event will return shortly. Please stay tuned.
We will be joined. We will give back to the people and make so. And we will enjoy the stories.
Enjoying the music? All content you're currently listening to was produced by Amazon's Audio Studios team. Stay tuned for your scheduled event. Want to host your own event? Create your meeting experience today at meetings.amazon.com. Thank you for your patience. Your event will return soon. Looking for caption support? Closed captions are available through the media player. We will be back shortly. Enjoy the background music as you wait for your event to return. Your event will return shortly. Please stay tuned.
Shiny bright lights. Shiny bright lights.
Enjoying the music? All content you're currently listening to was produced by Amazon's Audio Studios team. Stay tuned for your scheduled event. Want to host your own event? Create your meeting experience today at meetings.amazon.com.
Okay. Hello, everyone. All right, Team Iceberg. Cool and energetic, everyone. Is it loud? Is it working? Not very loud. Okay, Kitty.
Aha, there we go. Is it green for on? I did not know that. Oh, gotcha.
Yeah.
So you want us to speak in the microphone so that everybody can hear us?
Can you hear me out there?
Got it. All right,
Yep.
cool.
All right,
Hi,
let's
everybody.
kick it off.
All right.
Danny, all yours.
Cool. Hi, everybody. My name is Danny Lee. I'm a dev advocate at Databricks. I'm also from Delta Lake. Ooh. But no, we're here to do a very friendly conversation, so it's all good. So to show the friendly conversation, Jason and I are going to go ahead and have a nice quick chat. We're going to leave time for for y'all to go ahead and ask some questions too. But let's start. Jason, why don't you give us a little bit of a background on how you got into Iceberg in the first place? Because Dan did go ahead and talk about, hey, there were some vital stakeholders, I believe. Were you one of them?
Yeah, probably. So just by way of introductions, again, thank you all for being here and taking time for your days and traveling and doing all that. I'm Jason Reed. I worked at Netflix with Dan. In fact, we started at Netflix the same week. Dan, obviously on the sort of data platform infrastructure side. I was like more on the practitioner, data engineering, data science side of the house. So we were close peers. I am not a co-creator of Iceberg unless like giving requirements is it counts as being a creator. So my role was to basically yell at Dan and Ryan about all the problems that he enumerated earlier. Like when the meta store wasn't scaling or the correctness went sour and I got yelled at by Reed Hastings, who was the CEO at Netflix at the time, when the membership count was not right, and things of that nature, right? And so that flowed downhill, and as many of you probably know in this room, like infrastructure is where that lands. So that was in Dan's lap oftentimes. And yeah, Iceberg was the ultimate solve he came to me with, which I hated at first. Because as he mentioned, it was like a bunch of work for our teams to migrate from stuff that was otherwise working, except for like there were massive pain points that we were addressing, but otherwise it was migration efforts are so much fun, as again many of you in this room are probably very familiar with. But in hindsight, it was a very good decision. Set of technologies unlocked a lot of value for us. I'll talk more about that, but yeah, so I spent 8 years at Netflix with Dan, and then co-founded Tabular with him as well. So I've been on that same journey now at Databricks, where I work on the product team in the Open Lakehouse space, bringing all of these formats and catalogs and compute engines, metadata, all that goodness together to again help people get value out of this stuff we call data.
I don't know. I mean, I think the fact that you actually offered a lot of the requirements in the first place does, in fact, count for you to help create.
I'm gonna count
I
that.
bet you,
Yeah, I'm gonna count
you
that.
should count that.
Yeah.
Okay, but on to the questions. I guess the first thing I'd like to better understand, I'm sure the audience wants to better understand, is how has Apache Iceberg changed how now data engineering works in the first place, especially, from your perspective of the fact that you saw that happen, helped that happen in Netflix, and you're obviously had seen that happen with a lot of your customers at Tabular as well. So.
Yeah, so the biggest thing that we had to do is basically unlearn a bunch of bad habits that we that we learned as a result of trying to be very clever engineers in the Hadoop space. So as Dan also alluded to, on the infrastructure side, they were doing a bunch of work to engineer around a lot of the challenges that we were faced with. And we were doing the same thing on the data engineering side. We were trying to take our old patterns of doing ETL type workloads and reinventing them for doing them in Hadoop space. And we got ourselves down to file systems, and we got ourselves into partition management and all kinds of games that we were playing. And we learned all the things not to do. We cut ourselves on all the rough edges that Dan mentioned and bled to death many times over to learn them. And what that meant was there was a very small group of people who were really, really effective in that space. You had to know a lot about a lot of different low-level technologies to be an effective data engineer. And one of the great things about Iceberg is it really up-levels that. And so I think the biggest impact it has on data engineering is just making it accessible again to a much wider audience for them to be effective. You don't have to have like super low-level distributed systems engineers just to do ETL type workloads, which we were down doing. So the biggest boost we ended up getting at Netflix, and we solved a lot of the problems that Dan talked about. But from my perspective as a stakeholder, it was productivity for all of our data practitioners, the data engineers, data scientists, analysts. Getting back to just SQL works. Those basic things work, and you didn't have to worry about correctness problems. You didn't have to do a lot of low-level tuning to get performance out. And we got to shift a lot of problems back to the database, right? Like we had inherited a bunch of that stuff as data engineers, like, oh, what's the right parallelism for our Spark job, and what's the right file size and partitions, and we were dealing with all these low-level concerns that historically databases had been solving, but couldn't because of this like coordination problem because we didn't have table semantics. And so one of the first things we were able to do at Netflix when we got Iceberg was move all that stuff back to the database and get it out of the data engineering space. And that was a huge productivity boost across the board.
That's really cool. And then I guess one of the things, I'm sure plenty of people who have built their own systems like this, how long did it take actually initially to see the value add that because as you imply very strongly, there's a lot of work that had to be done in the first place. And you were originally against it too.
Yeah, totally against it. I hate migrations. I was like just finishing a Python 2 to 3 migration, which took us years to finish. And now you're telling me I have to migrate all my ETL pipelines to some new storage format. Yeah, so it takes time. And there was a lot of convincing of stakeholders, convincing of management. Like again, lots of folks in this room have probably been through that. The process is the same as has been in other migrations I've been a part of, which is, as Dan alluded to, you start with the ones who are willing participants because you're solving, a really core pain point for them. You build trust on those early successes. You leverage that to get the next wave of adopters, and then eventually, you get Jason to come around with a stick on the long tail and just beat them into using Iceberg. I think it was like a 5-year plus journey for Netflix to get all its stuff converted over. I think it's happened after I left. I think we finally finished. So I wasn't there for the party. But the productivity gains are diffuse. So it's hard to say it's not like some very acute thing that happens. But it was very real. And it shows up everywhere. How much time do we spend cleaning up data correctness problems once they happen, right? Because in these big data warehouse systems, you have all these ETL pipelines. You have one bad write to a table in some DAG, and then it just proliferates its way down the world until it's in some dashboard somewhere. And figuring out first just understanding how big the problem is, and then actually going and cleaning it up is weeks of data engineering time. So not having to do that, that's huge. So it's confidence in the business, saving trust from the business and the data you're producing matters a lot, and then just making us more productive. So it happened in a lot of different spaces like that, but it was significant.
No, makes sense. And do you have a particular favorite one that you can talk about, which, in terms of like the ball of metrics, like in other words, it used to take X number of weeks and now it's down to hours or something akin to that? I'm just curious.
I think I was most happy with the stuff that we got to throw away.
Oh, okay.
Right?
Yeah.
Like
All right.
the engineering that we had done, which was just pure tech debt because we're engineering around some problem that we just got, like, we don't have, we can throw, like, all this code and it goes away and it's now like Iceberg's gonna handle it. So a good example of that is, we did all this telemetry from Netflix, apps running on whatever bazillion devices across the world. And particularly like telemetry about the stream. He's like what the quality of the stream is and buffers and all that good stuff. And the devices have limited network capabilities, and so you get this data sometimes right away and sometimes like days or weeks later, so that the late arriving data problem. But all of it is like very, very relevant. We didn't want data dropping on the floor. But in the old style of like Hive style tables and partitions, it was very difficult to like take, you'd get data in that cover any given hour. You'd have data that goes back weeks or months, and you're trying to like shove that into now hundreds of partitions, little tiny files over and over again. So like if you've ever been in this space, like you understand the pain. And we engineered crazy solutions to this problem so that we could work with this data effectively. And then when we moved these pipelines over to Iceberg, like all that's just went away. It was gone. We don't have to think about it anymore. It was like, insert this data into my table, let it flow into the partition it flows into. I don't have to worry about it. If they're small files, the platform will clean it up later. I'm going to go back to doing, my normal job. So I got to treat this huge table with later having data like it was any other SQL table. That kind of stuff like is really, really valuable.
Makes a lot of sense. And then one of the things that I'm sure some folks are going to ask, so we figured we would go ahead and preemptively talk about it, is like, now that what do you think is the commitment for the Iceberg community, in terms of the open source community, now that you're, part of Databricks?
Yeah, sure. That's fair. I think it's the same. Not much changes. Like I've been obviously, watching and a fervent provider of requirements, and I ask for lots of things from Dan and Ryan and the team about what I'd like to see so we can unlock business value and business use cases. And that was true when I was at Netflix, and it was true when we were running Tabular. We were doing all the same things, and the contributions we were making to the open source project were in the same vein. Things like the REST catalog API is a good example of like something that came out of those efforts. Just because we were solving real world problems. And at Databricks, my day-to-day is very much the same. I'm constantly talking to customers, like hearing what their day-to-day business problems are and figuring out like what are things we can do in open source technologies and standards and formats to help solve those problems. So to me, to some extent, it's like, it feels very much the same.
Cool. And then based on that, you see this amazing effort by lots of different companies. Right, today it was Snowflake, Databricks, PubliGraph, and AWS, obviously. But then we're going to have more and more of these meetups. I'm just, what's the relationship like in terms of working with these various vendors that are actually trying to both cooperate with Iceberg and also leverage Iceberg for their own offerings?
Yeah, I'll be overly transparent here. I remember when Dan and Ryan were giving their first like Iceberg 101 talks to the data engineering team at Netflix, and like there was a room like half this size, maybe, right, of Netflix data engineering. That was like the beginnings of what would be considered an Iceberg meetup. And they were just like explaining these core concepts of what a table format was to all of us there. And to see from that, and here we are, and what I'm looking at today is mind blowing to me. Like I would have.
There's a crowd out there too.
Yeah, I would have like I was against this, right? So I would have never guessed that it would have evolved into this. That's amazing on one hand, and I think really, really challenging on the other. It's like, will it be a victim of its own success? I think that'll be interesting to see how the community. It's been an amazing community, continues to be, and I'm always like continually impressed that even as we add more people, more voices, more talent, that the velocity of the project continues to improve versus decelerate. I think that's a difficult thing to do. I give a ton of credit to just the community members. Like it really is like a group effort. Certainly, the committers and those folks, but I think everybody who's involved in discussions and even the folks like yourselves who put the meetups on and everybody behind the scenes that make this whole machine go, it takes that whole group of people working together. And that's really, really fun for me to be a part of. I'm just glad to be along for the ride.
Cool. And then the last question, I guess, before we open up for the audience is like the relationship with Iceberg, with and the community for that matter, with the various hyperscalers, whether it be the cloud hyperscalers or the data hyperscalers. This is being a little bit more specific than what I just referenced, but like, do you see as there's this hyper growth, this hyper interest, like what are the things that we can do to ensure that the community still grows the way you want to see it, while also the fact that it brings on its own new set of problems?
Yeah, I think that's a great question. And I think every project and every community is going to be different in that regard. I don't know that we can look at, certainly there's other open source projects, even Apache projects, which have had similar cycles. But I think every project is going to be independent. It's got its own set of users and community and problems it's solving. And so I think we're in uncharted territory a bit, and we'll have to sort of work together to figure it out. I think it's fantastic ultimately that you're seeing this participation from, say, like the hyperscalers. It's just a lot of validity for the whole community, and you wouldn't have this level of interest if that wasn't the case, and you wouldn't, like, standards really require like everybody coming to an agreement, and the value of Iceberg is really in that specification, the standardization, the interoperability. Like, that's what it was designed for originally. That continues to be its value today, and that's only, I think, solidified by other significant technology projects and vendors supporting it.
Perfect. Okay, well then that's for the preset one, but we definitely wanted to open up for questions. And so by all means, let's start passing out the mic and allow folks to actually ask questions now, please.
So we have been talking a lot about, say, how great performing of the Iceberg. So then is this like, would you recommend all the lake data or majority of data lake to converting insert into Iceberg, or there is some scenarios like best to use Iceberg, some may not need to?
Yeah, I think this is actually a great question. So just to rephrase, is Iceberg the right technology for all the data in your sort of lakehouse architecture, or do you think there should be a mixture? I'm probably biased, but I'm also going to try and be objective here, which is to say I think Iceberg's great for everything. It doesn't mean that you have to use it, but I do think it is designed to be generally applicable. Like, there will always be like niche use cases where you have very niche requirements where you need something more specialized. But in terms of generally speaking, for the vast majority of your analytic data sets, Iceberg's great. I mean, you saw the puppy graph folks, like they're running, and he didn't give a demo, which he should have. I've seen it. It's amazing. Like, graph queries, typical like historical graph queries, where you had to have very specialized storage and compute working together. Now working on top of just plain vanilla Iceberg tables. You can bring some Iceberg table you have, and you say like, oh, this represents my nodes, this is my edges. You like let puppy graph go, and it's fantastic, the performance you get out the other side. And so I do think like it's sort of a proof point that Iceberg's a great generalized storage form for analytics. I'm honestly surprised how well it's done in its performance as it's been adopted by even commercial engines, right? We see this time and time again where commercial engines with their proprietary formats, sure, of course they perform great. They should, they ought to, they're engineered to. But when they can get very similar performance characteristics on Iceberg tables, again, I think it's another proof point that it's just a good generalized solution to the problem. There's a lot more work that the Dana team are doing. So like, I think that's only going to get better. And this whole room, everybody's helping with that.
Is there any niche or place where you would say, no, Iceberg is not for this?
I'll reiterate, if it's not obvious, it's not a transactional database. And I say that just because it comes up and people try to use it like it's a transactional database system, like it's a Postgres. It's not. And you're gonna have a very bad time if you try and treat it like that. So I'm I want to believe that there's some future state where we have a singular thing that's your analytic and transactional. We've been chasing that nirvana for my entire career as a data person. I'll believe it when I see it. I'm a skeptic, but I was skeptical about Iceberg too, so I'm not saying it can't happen. I'm just saying I'm a skeptic and I'll, believe it when I see it. Yeah, all kinds of proposals. I'll be happy when that day arrives.
Yeah, I want to jump in. Like coming from SQL Server before this, I mean, like we all had that dream of the HTAP where like it's one system for everything. Yeah, we're not there. Simple.
Don't use Iceberg for your transactional.
Yeah. Let's not do that.
Quick question. So, on the catalog side, what's your thoughts on catalog federation, or you have multiple catalogs? So there's a catalog proliferation. Data is in multiple pieces, right? So, where are we going? Do you guys have any idea?
I have lots of ideas. So the question is like, what's with catalogs? Where are we going? Catalog proliferation, federation, etc. This is something obviously that was, we dealt with a lot at Tabular and still now, even my role at Databricks with something like Unity Catalog. What I see mostly is you get to a certain complexity of your organization, a certain size, a certain set of users who have different needs and preferences, et cetera. You have a variety of tools. Like to some extent, Iceberg is a manifestation of the fact that you've got a variety of tools, but we really only wanted one copy of data. So how do we get there? A variety of tools probably means a variety of catalogs. So I think, yeah, in big enterprises, you're going to end up with more than one, and federation is a natural way to continue to deliver on the promise of one copy of the data, which I still think a lot of us want to get to, but let various teams and use cases stay in the worlds that they're comfortable in. So I think that I expect to see that trend continue. Could be wrong about that. So I don't feel like it's an opinion weakly held at this point.
I mean, related to that, from your perspective, do you think we're starting to get those aspects into IRC in the first place, or do we feel that we still have to have more discussions in order to get to that point? Where we sort of agree on how a federation is even supposed to look like.
Yeah, I don't think we're at the point where we agree where a federation is supposed to look like. I'm really glad we're taking the first step of at least getting to like a consistent catalog API. So like the REST catalog API at least allows all this, these catalogs to have the same API. In which case, having multiple of them and having federation is not super painful. There are still some amount of pain that goes along with that, but it's a lot better than having multiple copies of data, having totally different formats. I think that's we've taken a significant step forward with Iceberg and with the REST catalog interface.
Cool. Any other questions?
Hello, I am a manager of data engineering team, so I'm used to having this arguing developers working over PR requests, and then approve them, argue again, etc. And I know that I always work against some deadlines, right? I'm just kind of wondering from outside, looking at the open source community, how does it work out to have a predictable timeline with such a kind of crowdsourcing model and, lots of opinionated, great, brilliant minds, I'm sure, behind that. How does it work out?
Yeah, so really the question is like, hey, in most of like our engineering world, software development, there's timelines, there's dates, there's deliverables, we're held to them. How does it work in open source communities when those things necessarily don't exist? And, we are having oftentimes vehement discussions and disagreements in order to like move the project forward. How do you have like any sort of guaranteed timelines? I think the answer is like you don't. There are no guaranteed timelines in open source. I think this is where again every project that I've been a part of works a little bit differently in terms of what they value in terms of speed versus consensus, quality versus sort of quantity, and another way to put that. I'd say the Iceberg community, and again, I'm not a core contributor of code, so I'm just a participant in the community, like many of us here. And also, given that I've worked with Dan and Ryan for a long time, so I sort of know them very intimately. they are very particular about, really well designed and implemented software and having really sound fundamentals and having consensus and making sure that we can solve the broadest set of problems with the most elegant solution technically is important to them more than it is getting something by a certain date. And to some extent, open source allows for that, which is kind of nice, right? And there are trade-offs to be had with that approach for sure. But again, when you're dealing with standards, I think that's also another place where that sort of being methodical is important.
Yeah, and just to add to Jason's point, I mean, an important aspect and why we're seeing the growth of the community in the first place is just because of the constant communication, right? There are arguments, there are conversations that are happening in multiple forums, and that's actually what makes it possible, right? That we know that, okay, we're getting closer, so then maybe I can take a bet on a timeline versus, okay, we're still pretty early, we're not in agreement at all. Okay, let's not take this on the timeline, right? I think that's an important thing to remember in all of this, so.
Yeah, there is definitely a meme that we call popcorn time when Ryan and Dan get to arguing about something very foundational, and the rest of us sit back and enjoy.
Oh, tell me. Yeah, he's go.
So obviously all the benefits of openness, both at the data layer and the catalog layer now, and all the just investment that's going into Iceberg is like a big boon for customers using it. But obviously there's a natural tension there with vendors who want to add differentiation that's proprietary. We've seen like different forms of that. I think we've maybe seen a little bit of that in RBAC. We've potentially seen that in terms of like table maintenance and like who can write to a table that's maintained by some engine that has great table maintenance built into it, right? Can there be many writers or just one writer, which kind of defeats some of the openness purpose? So I guess just with all your experience, what are the areas you think that are appropriate to have like vendor specific differentiation? Maybe through some like common plugin interface or something where it makes sense to have differing implementations. Is it around performance? Is it like, what are the areas where vendors can and should be able to differentiate?
That's a great question. So just to paraphrase again, openness is great, standards are great, but ultimately, not just across vendors, also again, just industry implementations, there's customization and differentiation that is inherent. And where is that most appropriate? Also, this is an opinion question. I'll give my opinion. I will say that I think one of the reasons that Iceberg was successful or has been is because it tries to not be very opinionated, as little as possible. And that I think is born from the fact that like it grew up at Netflix and it then ultimately was adopted by a lot of other like big tech industry companies that have a lot of already like baked in opinions of their own. Like how if you go into any one of these tech companies, as much as like their stacks are similar, they're also super unique in their own ways, right? Every single one of them. And so if there's going to be some technology that gets used across all of them, it has to be very adaptable. It has to be like not very opinionated so that the companies can apply all their own opinions on top. That's actually worked out well for commercial adoption for the product as well, because
that's the end users though. What about the vendors that build platforms?
Yes, same thing, right? So like it's that lack of opinion has ultimately helped, I think, it be adopted by the vendor community as well, because they've been able to imbue their own opinions and implementation details behind the specification, right? So there is a reference implementation of the specification in the project, but there's a lot of vendors who don't use the reference implementation. They like completely implement the spec from the ground up, and they're able to do that because the spec is very sound. And I think it's perfectly okay if they want to differentiate in that way, as long as they're adhering to the specification and they stay within it's interoperable.
In what ways though? Like
then that works.
In what ways you think it's good for them to differentiate, like performance or security or?
Yeah, I think it's a very like vendor specific question. Like how are they trying to bring value to the market? It might be they're trying to bring the best performance on object storage, open table formats, and that's how they're going to differentiate. It might be that they're trying to bring governance, and that's how they're, so I think different vendors will play into different aspects of that and try and, they're building value in their own way. I think that's healthy. And the good news is that I think any vendor who tries to do that but differentiates far enough away that it no longer becomes interoperable with the rest of the ecosystem, they kind of lose, in the sense that like that's the whole value of having these open standards in the first place. And so that standardization keeps the sort of the vendors at least aligned. And because it's like you can't generate value on top of the project if you go too far afield.
Thank you.
But I think everything is fair game ultimately. Like I think it's all bringing value to the ecosystem, and if you're delivering value to businesses and you can, monetize that, I don't think there's any problem with that.
Okay, time for one question. More question? Yeah.
So we've heard a lot about like analytical processing, batch processing in the context of Iceberg. What are your thoughts on like the real-time processing? Would it be possible to build something with Iceberg and object storage where, retrieval or writing, you can do stuff in basically real time? What are your thoughts on that?
Are you asking me if Iceberg can be a transactional database? I think I asked and answered, right? Sorry. In all seriousness, no, I think some of the stuff that Dan alluded to that the community is working on in terms of commit latencies, bringing those down, making it, to make smaller incremental changes more quickly, so you can do, stream processing is a big driver. The words real time or loaded, so I'm not even going to touch that, but stream processing use cases where honestly I think we've identified Iceberg isn't always fantastic and runs into limits pretty quickly. I think the community is aggressively trying to address those things, and there's absolutely room for that. Like as much as this is seeing all the success of Iceberg that we're here witnessing is fantastic, it's also like very much in its infancy. It hasn't been around very long as a technology. I think there's lots of room for places that it can improve. And I'm excited to see what happens in the next 5 years.
Yeah, one more.
Last one.
The last one.
For reals, last one.
Yep. For reals. Yeah.
So we have currently all the heavyweight compaction that we do with Spark. Is there any roadmap for some lightweight compaction methods in Iceberg?
So I think the question is, we do heavyweight compaction in Spark. Is there room for a lightweight compaction? And these are subjectives, like it's like what's big data, heavyweight versus lightweight. Everybody's got their own definition of that. I don't know, Dan, anything particular you want to like speak to there? I'm gonna bring you out of the audience.
It's kind of a question in my domain area. I would say that like there are utilities are available in Spark for compaction, and those actually can be used for both heavyweight and lightweight compaction. In fact, you can do very targeted compaction on partitions or based on filters and things like that. So I think that there's probably ways that you can further optimize those, and it may take even more specialization. But it's entirely possible. Be a great contribution.
A lot of the compaction
Good answer.
is actually in core, so all of the logic that determines what has to be compacted is actually a part of the.
Anton, you're going to need to say that all over again with the mic.
Just to add a few cents, I think a lot of the core compaction logic is already available through the library, so that's what Spark uses. The only bit that it supplies is the distributed job part of it, but the logic that determines what has to be compacted, the rules, they are actually part of the core library. And Flink, for instance, tries to use that to provide the Flink compaction in any engine, or if it's a lightweight compaction, you can probably do it within like a single node process if you want to.
All right. Well, then go for it. Yeah.
Yeah, I think this is really good. Thank you, Jason and Danny. I think this is amazing. It feels like we should do these fireside chats maybe every week, like Friday, and just bring like light food and drinks like wine and beer and maybe some chips over there, right? And make it a point, spend the evening iceberging or something, So very cool. Thank you very much. And so let's move on to the next session. Sandeep, he is one of our product managers here. He's been working diligently on a lot of different techs, including the security component, also on the cataloging, federated catalog as well. So we're going to start with this session.
All right. Hi, everyone. I'm Sandeep. I came long way, fourth floor to here. And thanks for everyone for coming here. I think organizers did a great job in arranging this meet, and it's great to see all the founders of Iceberg right here. So I'll be talking about the optimizing, what we're doing in optimizing the Iceberg query performance by doing the kind of heavy lifting of generating the NDVs. Right? So I'm going to start the presentation like at 10,000 feet level, just talk about some of the lakehouse aspects, some of the reInvent launch, and then go deep down into what is cost-based optimizers, what the Iceberg stats provide, and what are we doing in terms of kind of helping customers to kind of make use of those stats, make the query perform. And I want to start a discussion about like what can we do about Iceberg stats? Can we actually improve the performance stats? We have a lot of ideas. I know the community has a lot of ideas. So just about me, I'm one of the PMs on the Glue Catalog Lake Formation side. Actually, our team is some of the engineers, brains behind this are right here, who helped launch Iceberg Stats, Iceberg Optimization, as well as some of the federation as part of the Lakehouse. I love working with the data, I love working with the community. Yeah, great to be here. All right, so Lakehouse. Before that, just how many of you use the Iceberg REST catalog? All right, some of you. How about Iceberg Stats? Okay, we have one person. And then, and what about Iceberg Optimization? All right, one more, same person. All right, so Lakehouse is the AWS offering that brings everything together, right? So it provides this Iceberg REST API interface. Your data could be in, S3 general purpose bucket, in S3 table buckets, or it could be in the Redshift warehouse in your own specific RMS or Redshift managed storage. Doesn't really matter because you now have the Iceberg REST APIs that you can use, and you can use any of the query engines or your own Spark or other engines to get access to the data. So we are really excited about this open API support. And we also kind of extended that. This is some of the still preview version, but kind of providing a single view to the data wherever it is, right? So that's what we call Lakehouse. Is your data could be in actual data lake, in the warehouse, in the federated catalogs. We want to enable it by bringing the best of the Iceberg in the Lakehouse by providing those kind of APIs, where you can use any of the analytical engines, whether it's Redshift, Athena, and start using the best of the Iceberg. So I'll be focusing this talk on the aspects, primarily focusing on the cost-based optimizer, which is what the analytical engines such as Trino or Redshift or Athena uses. And what does it need in terms of Iceberg capability, particularly the NDVs that they need to build the optimized queries, right? So let's go a little bit deeper. I talked about cost-based optimizer, but never really defined it. I think for those who are coming from the database side of the world, this concept has been there for a long time, right? So you have the query, and the cost-based optimizer is an inherent part of any of this engine, and which determines what is the best way to run this query. And it does that by generating multiple query plans, right? And then after generating multiple query plans, it needs to select which is the most efficient query plan to run. And for that, it needs to know it needs to know the statistics behind it, right? To compute the cardinality and to define and to select which is the most cost-efficient plan. And there are multiple techniques that is there in the open source engines like Trinos or Spark or Redshift, and many of these techniques boil down to how do you kind of reorder the joins? How do you do filtering earlier so that you can have have the rows which are already filtered, and you don't need to kind of join this kind of large billion row tables. Rather, you can join first the table with the lower dimension, right? But how do this CBO succeed without knowing the basic thing, which is the table stats? In the database world, we took it for granted, right? Every table has those kind of things. But now when you come to Iceberg tables, does it have it, right? I think that's the question that that we are now asking. Okay, we have the Iceberg. Does it do the stats so that my optimizers work? And so let's go and look at the Iceberg table layout, right? We all are familiar with it. You have this Iceberg catalog, which can be your glue catalog, pointing to the reference to your metadata file, which points to your manifest file, which has a list of the manifest manifest list, which has a list of manifest files and contains the data. And each of these layer, right, you have some stats available, right? So manifest list has certain stats about how many row counts, max, mins. Your manifest has a bunch of stats, right, which is record count, the nulls, max, min, etc. And these are very important stats, right? Because when the query executes, it looks at these stats and determines, okay, do I need to go and really access that data or not? And if I know these stats, which most of the Iceberg kind of populates in most of the time, your queries are pretty efficient in terms of execution. But now, if you think about cost-based optimizer, these file-level stats are not sufficient, right? You need table-level stats because you are making the query plan across the multiple tables. And so what is that Iceberg provides in terms of kind of helping us get those table-level stats? So there's this concept, I think the V2 was launched, which is called puffin file, right? So puffin file is a very simple specification. It is basically a list of blobs of data which is kept outside of the structure that we saw, right? So we saw the structure of metadata, manifest, and others. But this file, the puffin file, is kept separately because your NDVs, and maybe you can in the future add additional statistics, can be a large data set, and you don't want to be in those set of manifest files. So it's kept separately, and then you can populate those puffin files. And as long as those puffin files has a way where the NDVs, the number of distinct values, are captured, you can analytical engines can pick it up, right? And the way it picks up is pretty straightforward. Your catalog knows how to go to metadata, and the metadata has a representation of statistics, right? So you go in the statistic, you see this is a statistic file here, and it tells you, okay, this is a file that has this sketch. And in this particular case, the sketch is a theta sketch, which is what the standard Iceberg supports. And this is where the NDV values are, right? So, and your Redshift, Athena can just pick it up from there. So it's great in terms of spec, but do this gets populated, right? That's the question we asked. That's the question the customer kept on asking us. And we found that there were not really good writers at that time when we started working on it. The Trino now supports the writing of the NDV file or creation of the puffin file, but there is not a huge lot of writers who build this. So in this case, basically we decided, okay, this is a part where customers can go and kind of generate these puffin files, which means there's kind of heavy lifting, right? You need to look at the changes in the data. You need to kind of build your sketch because that's the compute-intensive ways of generating the stats. You need to populate the puffin stats. You need to kind of populate the metadata references. And then you need to make sure that analytical engines are default integrated so that their queries are optimized. And so that's kind of the heavy lifting. We thought that something that we should do it. And so this was something that we launched as part of the Glue Catalog feature and integrated with the 1P engines and analytical engines like Redshift, Athena. It's available to everyone, right? So it's in the puffin file. So you can have your own engine, can grab those NDV stats and use it in your optimizers, right? And then more recently with the Lakehouse, where we are kind of moving towards the catalog level concepts, right? So these are multi-catalog level concepts where you can have the catalogs and have number of tables in it. We extended this concept to go at the catalog level, right? So you don't even need to do it at the table level. You just go and say, for this catalog, I want any of these tables to be optimized. And anytime the new tables get created, we watch for it. New tables get created or tables get modified. We look for it. We identify changes, and then we generate a stats on it. So we do all those heavy lifting for you and keep it maintained, right? So that's the key piece of it, to keep it maintained. And then there's a default integration with the analytic engines. And we do it for Iceberg, of course. We do it for other file formats as well, right? So and it's as simple as you go to the catalog level and catalog say, I want to just turn on, make this manage the table statistics for me, and that's a kind of simple option you have, and you just kind of provide that option, and then don't worry about the kind of doing it at the table level. And what happens as you create a new table, right, is you can go and look at the table, and you'll see that, okay, your statistics are getting created or generated for those tables. For example, in this case, the schedule is auto. When it's generated, when it's created, what are the NDV values for different columns, right? Those are available to you if you want to look at it. But more importantly, they are available to analytical engines, right? So these analytical engines will look at it, they access it, and then they do the real work, which is actually find a query plan, which is the best efficient plan for this. And the question is does that really work, right? So we tried to do some benchmarking on this. And we found that we did it on the industry data sets like TPCDS data sets, and we ran through a bunch of queries and scenarios and all that. And we found that just having this performance stats, basically NDVs, help us improve the query performance by between like 30 to 80%, right? Which is not bad. Like this is someone doing the job of keeping this table maintained and managed, and you get this up to 80% query performance improvement. Why not, right? And this actually is public blog, so you can go and kind of recreate the environment and maybe not standard based, but maybe run it on your queries and see if you get kind of the query performance improvement. We did it on the other engines like Athena as well, and we are seeing like between 30 to 60% improvement on those queries, right? So we are really excited about the kind of results we are seeing and kind of ability to make these make the Iceberg, which works great, but it can work even greater, even performant by having some of these knobs added. And that's where we want to kind of work with the community, right? Like what is that kind of set of optimizations or the set of additional statistics, secondary indexes that could help in improving the queries further, right? Some of the things that we tried out and we are kind of researching this all the time is, okay, what about right now is supporting theta sketches? What about HLS sketches? Can they be more performant? Can they be more, can we do it even faster with those? What about the additional statistics type, right? So in the database world, the histograms, MCVs are pretty common. What if we build those and add those as part of Iceberg spec? I mean, this requires change to spec because the current spec is only NDV only, right? So we need to kind of improve the spec. What about additional indexes, right? Like how if we can standardize on some of the additional indexes which are common, that will provide us the kind of query efficiency that we are looking for may not be needed for all the workloads, but for some workloads, the efficiency could be really high. So we want to see if the community has kind of appetite for kind of improving that and work with you guys on this. The other aspect is we think that the table statistics in general are, in a sense, table stakes, right? In the database world, we assume that it is there, right? But in the data lake world, as you can see from this room, like only kind of few persons know about it, and not many. I would think that not many have those stats on their tables. And there was this question about kind of differentiation and all that, right? And we have seen some vendors kind of putting their stats in their own proprietary ways, which is not available to others. So we want to ensure that stats are open, they are very cost effective. Over the period of time, we think that should be free to everyone. And we want to drive down those generational stats to as low cost as possible, to the zero, right? And so we are making kind of as part of our thing, our plans kind of driving the cost in terms of compute costs by using different ways of compute and all that. And we want to kind of work with the community to see if there are other ways to do it. For example, your catalog knows a lot about what's happening on the data side, right? If we can get those signals out and use those, can those be used as a way for kind of having that intelligence to build what stats is actually needed? And so there are aspects of maybe their catalog level, maybe their query engine level, but there is aspects of kind of that intelligence which is currently lacking and which could be standardized in a sense, which will be available to everyone, right? So we want to kind of have the community think in terms of that. Yeah, so we are really excited about this. I know there are a bunch of things we want to talk about in terms of Iceberg risk catalog, stats, and optimization. But this one I wanted to focus on one of the key things, which is really the query performance. So thanks. Any questions? And we have some of our engineers back here, so I can direct the technical questions, some of those to our engineers too as well.
The question that I have is like, so this is more like an additional steps on generating a stats, right? So the default, the compaction procedure, say what Spark provides or the other engines, does it or it's native to AWS only or not?
So this is nothing, so yeah, so you can generate a stats, right? Puffin stat is the open standard. So you can generate that. You can use the Spark procedure, create and build your own ways of writing Puffin files. Kind of create your own sketch based on your data and write a Puffin file and make sure you populate that, all that, right? So that's something that is, you can do it similar to how you did it for the compaction for the Spark job. From the AWS side, we kind of help in kind of taking the heavy lifting out, right? So for Glue Catalog, for example, we provide the compaction, which takes care of aspects of if there are changes happening on a partition, we look at a partition and say, okay, if there are more than 100 changes, then I will go and compact this particular partition, right? In a similar way, this stats feature is like that, is we look at the changes in the data or by schedule, and we build the Puffin file. So this is something that we provide as a kind of as a value add. It's something that you can build yourself as well.
Follow-up question is like, because the data is neutral in a common place, like there could be several engines that operate and keep updating the data, right? So it means like, there's some automated process that runs in AWS that constantly keeps updating this Puffin file, or I as a person have to schedule something so that.
Yeah, so this is what we build as a, yeah, so the question was like, does the AWS help in automation? So yeah, the answer is yes. Yeah, so when you have this catalog level property, right? You say, okay, I want to keep this catalog performant. Any new tables get created, we will enroll them, we'll schedule the stat generation for them, and we'll keep them updated, right? So that this automation is what we provide as part of it.
Very good. Any other questions? Yeah.
Is there like any API or trigger to know when the compaction has happened?
Yeah, so so when the compaction happens, right, there's a kind of snapshot gets created, right? And the Glue Catalog has set of APIs that provides a way of you knowing the changes to the data, right? So when the table is updated, table is changed, and all that. So you can look at the events from the Glue Data Catalog perspective in terms of what is changed. Okay. I don't know, Carl, do you want to add anything?
The reason for like asking this question. In your Iceberg table, if you're using Glue Catalog to publish events to like that. Now, here in a sense, compaction, we can submit a bar request. This is something that our team can work on publishing also. Same thing with Puffin file generation as well.
Yeah. So yeah, and we emit the events for example, for the compaction, snapshot retention, or orphan file deletions. Those are some of the optimizers or maintenance activities that we support. Those events are emitted to the CloudWatch logs that you can take a look at. Yeah.
reason for asking this is like we use the glue catalog and other services. For instance, like in Snowflake, we have been using the glue catalog. So in those cases, we get to know like when the metadata has changed or when the compaction changed. We need to like refresh the other sources or the table in Snowflake. So we
I
just
see.
want to know like if is there like any event that is being like emitted so that we can follow that, like refresh the.
Yes, I can follow up and provide you the kind of spec on and the APIs on that. Yeah.
Okay, thank you so much.
Okay, one more question. Okay, hang on.
So do any other query engines like Trino or Spark, can they use these stats and do they use?
Yeah. So the question was about the Trino and use of the stats. So yeah, the Trino has built-in integration. By default is off, right? So you need to kind of ensure that when you use Trino and you need to enable that. Or maybe
The stats, I mean, the Puffin stuff was added by a Trino contributor. They're on by default. If you write through Trino, you automatically get the stats created.
Okay, it's on by default. Okay.
Yeah, it's a critical part to have good good results.
Yeah.
And every engine should write them as they're writing them. It shouldn't just be Trino. I don't know if Spark does, but it absolutely should because they're critical to performance.
Like, is it always up to date or it's async?
They're collected as part of the writing query, as they should be. I don't know.
Along those lines, should we make the min-max? I think as of now, the manifest says min-max are optional. Is ever it going to be a required field?
I will, as the founders.
Should they make min-max stats optional? Or I mean required.
Required.
Yeah, I mean ideally you would, but
They're also not the min-max. They are a bound on the outside, and you can't use them to like return faster results. The min is guaranteed to be a value smaller than the minimum value because for like strings, they're often truncated. Making them required might put undue constraints on like streaming engines. It might be really hard. There's lots of problems where it doesn't work, but if you can collect them, you absolutely should.
There's also a lot of challenges with like positional deletes that may invalidate some of those values. So there's, equality deletes, positional deletes. There's so many cases where you can't really trust it to just like grab the max and say, oh, there's the result. You'll probably get it wrong sometime.
To maintain that min-max.
Just small comments, like it's maintaining those min-max of the entire table, especially it's a huge, super large, will be expensive.
You can reach good performance with approximate numbers. You don't have to present precise.
Exactly. Right.
It's okay to be wrong.
Yeah. Yeah, the sketches are approximate. Yeah.
All right, very good. Thank you, Sandeep. This was amazing. All right, so the next talk is Awa. You are. I have to give you like an inside story. All the Iceberg meetups that we've done over the last probably 6 to 8 months, he's been the rock behind all of this. We would have not done any of these if Awa was not there. Just to kind of let you guys know, and he's very humble. Which all right, so I think most of you know him. He's a PMC member. He is. Your talk is on variant metadata.
Actually, I'm not. No, I'm not. Well, yeah, I'm a HAM PMC, but not Iceberg. I'm just new to Iceberg, actually. Do I have slides? Sorry, how can I find it? Oh, yeah. Yeah, my name is Aihua. I work for Snowflake and on Data Lake, basically Iceberg team. Yeah, actually, I worked on Hive, HDFS, and Yarn before, but recently joined, like actually 2 years ago, joined Snowflake, and right now actually tried to work on Data Lake and Iceberg. And currently, I try to work on variant-related stuff. That's kind of like we are collaborating with open source, try to drive that, especially like with Databricks folks like Daniel. Today, I'm gonna take this opportunity to give an update on variant and especially on the metadata side. Uh, um, yeah, here's the agenda. So basically, I'm going to give some introduction and background on the variant data types and shredding. Then some part of like a metadata. And later, we're going to talk about some metadata enhancement and also like project progress. Yeah, I think it's already kind of a long day. Hopefully, you guys still feel like energized. But of course, at night, like we're going to have very good food. Yeah, today. Yeah, first, like, what is a variant data type? At Snowflake, actually, we already support a variant for a long time, actually, for internal format. When we start to support Iceberg, actually, we got a lot of asks, can we add to Iceberg? Without that, we cannot migrate to variant. We cannot migrate to Icebergs. Of course, to Iceberg, it's for obvious reason, right? They don't want to log to a particular vendors. That's kind of like major reasons. So that's why like we start to propose the open source and then continue to drive forward. So like variant, it's kind of like to represent a semi-structured type. I think like Daniel or we kind of like give a little bit of a variant. So it's kind of like to represent semi-structured data. For example, XML or like JSON. Actually, most like a JSON data type. Of course, for variant, it's not only to store, let's say JSON, or like you can store primitive types as well in variant. Basically, variant arrays objects can be stored in variants. Like why we kind of like try to introduce variant in Iceberg? Of course, one, as I mentioned, a lot of asks from the community. Try to achieve like parity with other engines. Like I know Redshift also have like similar concept of like super data types, which is a variant. Snowflake also supports variant as well. And Spark actually recently just add variant support. To add to Iceberg, the benefits of that is, we're gonna standardize encoding, decoding, and standardize like shredding those kind of specs rather than each engine to introduce its own formats, right? Which will cause like compatibility issues. Like if you want to move from one to the other, then you have to kind of load the data. While we standardize the variant data type in Iceberg, then you don't have to kind of you point to a single. It's kind of like single copy. The third one is, of course, we can support many more scenarios, which involves semi-structured data. Some high-level tasks for variants. In order to support a variant, we need to support like encoding, decoding. We have to define the format for variants. The second area is shredding or subcolumnization. Actually, at Snowflake, it's called a subcolumnization. The shredding actually is kind of like for the optimization. Without shredding, you can have like variant to work. You can read and write variants, but shredding is kind of bring to a next level, which is like you kind of extract the data from variant data to store as a separate columns. That's kind of like, I'm gonna talk a little bit more later. We can have like additional metadata. With that, we can do more optimizations. Yeah, so third is like a metadata enhancement. Of course, it's kind of like high level things. We have way more around Iceberg. Like for example, if you want support in Parquet, right, you have to add the types in Parquet or in Avro. Through the talk, maybe I'm gonna use this kind of examples. So I'm gonna like just use like some data to show what does it mean, for a variant. So as you can see, like we may have like different format. Let's say for ingestion applications, right? You receive some events. Like for example, event type, it could be a string type, or could it be a integer, or could it be a long, right? Or you could receive an error response. It's kind of like it's not the same data format. So that is kind of like a good use case for a variant. You kind of load that into one column, and then later on the during the read time, you kind of like parse that out based on, it's kind of like parse time, you can have a schema. And here I also kind of include a nested array and objects as well, just like to show how it looks like. Like when you try to use, here is example. You can create a table with variant column, and then if it's a JSON, you can just like pass JSON, to load the data. During the query, you can use such kind of like format, to access a sub column or sub fields, and convert that to, let's say, string or double, based on stored data. Of course, this is kind of like a Snowflake format. Spark actually has a slightly different syntax. So then let's come into the encoding, decoding part. We use for basic variant support, it's stored in two binaries. One is a value, one is metadata. There's two fields. Like the data, as we mentioned before, like primitive type, array type, or objects can be stored in variant. For primitive type, each of them has a type code. Of course, for details, you can get to this link to find more information, but it's kind of like just like give like very high level introduction. We can store int or string in a value data. For arrays, it's a little more complicated, but I refer to the spec for detail. Like for object keys, now we know like the keys will be duplicated, right? If we if we store the keys, strings in the values, then the value field will get large. So what we do is we're gonna encode the key, object key in the metadata as a dictionary. So for example, key event type, we're gonna store that in this dictionary with ID 1. And then we can, in the value itself, we can refer to that ID rather than event type in the value. So that's kind of like for space saving. Yeah, that's kind of like a basic encoding. Now let's talk about shredding. Like with just like basic, with just a basic variant encoding, decoding, we already can achieve some of the performance improvements because of the like encoding methodology. We don't have to scan or load the whole data to access one field. We already can do that, but shredding is one step ahead to kind of like extract fields as a separate column. We call it subcolumn. With that, we can achieve, a couple other benefits. For example, file pruning. We're gonna also build the metadata. I think Sandeep also kind of like talk a little bit of like metadata, right? So for subcolumn, we're gonna also do the same thing. We're gonna like collect the metadata. With that, we can prune the files, which is like not falling into the min-max, for example. And also, because we extracted the subcolumns, when we try to access a subfield, right, you don't have to access the whole variant data. We just access the subfield column. So that's kind of like reduce the data access. The third one is storage optimization. If you store the variant alone, it's just like binary, right? There's no pattern or something. Then pretty much you cannot do optimization, let's say on the Parquet or like org level. But if you extract the subcolumns, for example, event types, right? Or it's logging, or log out, those kind of things, right? Then Parquet, I think we can do like more optimization and save storage. Like here is like a shredding process. Basically, for each file, let's say for a column, we have like 1,000 or 1,000 columns, right? 1,000 data. Now, like how do we like shred subcolumns out? So basically, we're gonna based on those 1,000 columns, 1,000 data, to decide what kind of fields we can shred. So that is kind of like engine specific thing. It's not like in a spec. Actually, spec doesn't define that. For example, Snowflake or Spark, actually they may use like different algorithms to do that. One other example may be like I'm gonna choose top 100 fields, which like the path, right, which is top 100 fields appeared in the data, something like that. Or maybe as simple as I'm gonna use the first variant data I'm seeing, right? All the paths I'm seeing in there, I'm gonna extract, something like that. The second task is like to determine the shredding type. So as I showed like in the previous examples, right? For example, event type can be string or can be int. Now, how do we decide which type to use? one example can be most common types. I can see like a lot of strings. Then for event type, then maybe I can choose string as shredding type. The third one is I can extract the values, shred the values into subcolumns. So basically, if the field value match the shredding type, then I can shred that into typed column. What that means is, let's say for event type, I shred into string, right? And the value is login, it's a string. Then I'm gonna put that into shredded typed column, string column. With that, you know, if everything is string types, we can collect the min max or all those kind of stats. So it's just it's going to work as a regular column, right, to do a lot of optimizations. Now, if somehow some of the data cannot be shredded, then the remainings will be encoded in its original data type. For example, 1, right? Event type equals 1. It's int. It cannot be shredded. Then it's going to be encoded in untyped column, which is still like int type. Yeah, here maybe like I'm gonna give an example. Maybe it can be a little bit easier to understand. So let's say the engines decide, oh, event type, I'm gonna shred it to string, and an event timestamp, shred to string timestamp. Email is shred to string. Here you can see like event type. This is like typed column. We're going to have like login in this column. Similar for event timestamp. Now, since we are not shredding note column, then it will be saved in an untyped column, which is kind of like the binary. Then you cannot do further optimization with this column. As I mentioned, since this is a 1, right? Event type is 1. Then when we shred this, it will be kind of null. We will not be shredded, and then it will be saved in untyped field. Yeah. Now let's come into the metadata. Of course, Iceberg has like file-level metadata or table-level metadata, but this doesn't change with variant. I'm gonna more focus on like column metadata. For example, like we have like value counts, non-value counts, min max, lower bounds and up bounds. Those metadata can be used for like file pruning or aggregate functions. But just as we mentioned, let's say Parquet, right? It may not have exact min max. It has a field to say, oh, if this exact or not. But I think the Iceberg doesn't have that yet. So I think we just like still use that. Maybe in the future, we can still, we're gonna add that kind of support, say, whether this aggregates or lower bounds or up bounds is exact or not. So when we collect subcolumn metadata, then we're gonna achieve the same benefits for subcolumns. Here, I kind of listed like 2 examples which can benefit from subcolumn metadata. For example, if you can have those kind of filtering, right? If it doesn't match this condition, then the files can be pruned. Or we can have this aggregate functions. So for like column metadata, it's stored in Iceberg manifest files. And the type, like we store like map to column. We store like a map of column ID to stats. For example, for lower bounds, it's a column ID to lower bounds. Because the data can have different types, right? So we convert that to binary. For null-value counts and value counts and the others, it's kind of like long, it's a long. Yeah, please observe that it's kind of like binary. Because of that, what in B3, right, what we are trying to propose is for subcolumn metadata, we're gonna collect lower bounds and upper bounds for subcolumns. And then we try to encode them into a single variant. Yeah, something like this. Like, let's say for event type, it's all strings, right? We're gonna have a string type and then the path, and we have a lower bound in here. Then we're gonna encode for each variant all the subcolumn metadata encoded into variant, a single variant, and then convert that into binary. With that, as we just mentioned, since it's a binary, we will not introduce compatibility issue in B3. For like other stats, like value counts, if we want to introduce in V3, then it's gonna break. It's gonna have a compatibility issue because currently it's a long type. It's not a binary or something. Now, for metadata generation, here are some of here like are the scenarios. If for a subcolumn, if all the types, it's kind of like on the file level for each file. If all the types are, let's say, string for event type, then we're gonna collect the lower and upper bounds. Or it's an integer, right? We can collect the lower and upper bounds. Now, if it contains multiple types, for example, it has string or int, then we're gonna skip. We will not say, we will not save bonds. We will not collect bonds because even you collect, you cannot use that. You have to like, because of the type promotion, right? You have to check. You cannot directly use the metadata. You have to check the column, the data, and then see if you can promote to the types you are using, you need. Now, if some values are null or missing, we still collect that because that's still kind of like valid. We can still use that to do to do like pruning or answer aggregate function. For the future improvements, this is more like targeted for B4. That's what we are thinking. We're going to try to expand the support to additional stats like value counts or null counts. I guess like that's going to be incompatible change. So that's like why we are trying to push for like in V4. And also in V3, they probably will not have like type promotion because for lower bounds and up bounds, we don't save the type in manifest file. Now, because of that, well, currently we have a certain type of promotion paths for Iceberg types. For example, from int to long, then we kind of use the data width to induce what is your original type. But that is not true for variant because a variant size can be, I forgot how many bytes to like very large bytes. many bytes. So we don't know like what is a original type is variant, or if it's an int, or if it's a long type. We don't know. So that's why we will not support type promotion in V3. But in V4, right, we can think of like store data type in bonds, possibly. With that, we know, oh, what is your original type? What is your new type for each file? Of course, we need to handle incompatibility because it will not be compatible with like V1, V2, V3. Yeah, here is kind of like thinking, how we're gonna store like stats. One, probably it's kind of like similar as what are we gonna do in V3. We can store them in a variant, or since it's an incompatible change, maybe you can do like a big change, which will like kind of group all the column stats in one structure, and then I'm gonna have like column ID to column stats. Yeah, but I think we need more discussion on that. Yeah, here are some like real world use cases. Yeah, one probably like ingestion, right? Data ingestion. If you want to ingest the sensor data or something, which like if it's a unique schema, then probably you can use like kind of like a table, right, to handle that. But if it's let's say for example it's a mixed, you have like errors or something. Instead of like add the logic in your application, maybe you can load that into a single column, a single variant column, and then later, you can handle. Let's say I want to handle errors, or I want to handle like type like version 1 event or version 2 event. You can do that separately. And also, for example, there's logs, right? A website logs probably varies a lot. Then you can load that into variant data type, variant columns as well. Here is like, I want to report the current progress. The first is like a spec. Actually, we kind of like adopt Spark variant. Initially, we were thinking, maybe Snowflake has its own implementation. It's proprietary, right? We can propose that. But Spark already have an open source implementation and a spec. So we're kind of debating, which one to do, to propose. Later, we think, oh, maybe just go forward with Spark version. It's kind of like similar. So we don't want to introduce a lot of like debate on that. So right now, the initial version from Spark is already in Parquet. Oh, actually, the spec is in Parquet. It's not in Iceberg. And we are also like working on improved version. And right now, it's under review. Second is like variant data type support. That's kind of like basic variant type support without shredding. The type is already added, and like a reference encoding or decoding implementation is already merged. We have like encoding is under review as well. Of course, if we want to support the full stack, we have to add support to Iceberg, Parquet or Core, a lot of like libraries. It's still going. Yeah, for shredding, actually, we kind of like started, but it's just started. Yeah, right now we are working on like a metadata part and try to do POCs, and also we need to add like shredding and reconstruction, because when you shred to multiple subcolumns, right? But what about I want to select event, right, which is the full variant, right? And to reconstruct the variant data. The last is like we need to do like integration with Spark or all kinds of engines. Like different engines, of course, needs to add that support at the implementation. And also like if you want to export to Parquet or Variant, then those storage needs to add logical type. Finally, this is a community effort to drive this project. I'm just like contribute a little bit on that. If you want to contribute, you can reach out. Of course, Dan also shared community link, right? You can also reach out to us from there. Here are some of the references. Yeah, actually, there are more of that, but this is a kind of like more related ones. Yeah, I think that's pretty much pretty much it. This is an ongoing effort, so hopefully after some time, I'm gonna report back on the development. Yeah, let me know if you have any questions.
So you mentioned that there's a spec. I assume this has to be rolled up into the larger like Iceberg V3 or V4 spec. What parts are you targeting for which specs? Like, I assume that since shredding is very new, that maybe the V3 would just have the first part, or like, what are the thoughts on how this will roll out?
Yeah, maybe.
I mean, like, I'm not asking for guarantees. I'm like, guess.
Yeah.
Like,
so
what's the feeling? What are the vibes?
Yeah, I mean,
Let's go with
in
that.
the Parquet community, and the first part of it is like adopting the spec in Parquet because we want to make sure that we have consistent representations at that level. And so, right now, the conversation is about wanting to adopt both the variant specification and the shredding specification at the same time, because they're close enough, and we would like to get to a point where they're both being used. So they are pretty close. I think that there's some small subtle things that we're working on in terms of the shredding specification and just formalizing that. It's a big community effort. We're working with Google and Snowflake and Databricks and everybody to try and nail that down. But the intent is actually to kind of roll them at the same time.
And like V3, V4?
As part of V3.
Okay.
Yeah, so right now, Parquet requires some reference implementations, and so we're working on donating one of the existing Java ones from Spark and getting that up to speed. And then we're looking for other implementations, and there's been discussion in both like Arrow community around Rust or C++, and there's also a Python implementation out there that we're looking at. So it's just kind of a matter of like, when can we get enough reference implementations to satisfy the Parquet community's requirement of multiple implementations.
And bailing on Orc?
We would love to have somebody contribute from org.
Not me.
Yeah, actually, when we propose, we were thinking of just add the variant data type first, but the community side need to combine both because they see the benefits of shredding. They were saying, oh, without shredding, probably it's not that much of use, so we'll try to combine them in together. Yeah.
It's a big lift.
Yeah, that's true. Yeah.
So you mentioned about shredding that you're going to be shredding like top 100 fields or something like that. How is that top determined? Like, is that based on the frequency of access or just in the order?
It's not well, actually, you cannot have access because that's happened during write the files, right? So basically, it's based on the field, the paths, how many paths have occurs in let's say 1,000 data. Let's say if event type happens 1,000 times in all the data, right? Then maybe it's a candidate. Do you follow what I mean? So basically, based on how, the occurrence in each of this data. It's not about access.
Okay.
At that time, it's not it's write time. It's not read time. Yeah.
And is there a way for customers to give a hint, like what fields you can shred and their data types?
Sorry. What was that?
Is there a way for customers to provide a hint, which fields you should shred and what should be their data
Yeah.
types?
Well, that's kind of like well, of course, this is up to the engine to do that. It's not in the spec. Spec actually doesn't provide that. So yeah, if engines implements that, of course you can do that. Yeah, there was some kind of a discussion about that. Maybe like, for example, whether I should limit number of fields, right? Something like that, or give a hint on like what kind of paths, or maybe I specify which fields should be shredded. Yeah, that's all up to the engine, actually. Yeah.
Thank you.
Yeah, thank you.
So, follow-on question to that. Follow-on question to that. So on the shredding, is there a downside? Like you don't want to shred everything, but you want to shred only columns that are interesting from a query, like predicates, joins, and so on. So just follow on to that question is that true? There is a downside to shredding too much and being able to, after ingestion, actually being able to specify based on the workload that these are the interesting columns.
Yeah, so for example, one downside I can think of is like you need to collect the metadata, right? And then that metadata gonna be stored in, let's say, manifest file. Then that manifest file gonna be large, right? I think it's in Daniel's presentation, right? I mentioned, like large manifest file, right? That's gonna be a downside, for example. Let's say before you only have like 100 columns, but now with variants, let's say you have like 10 variants, and each of them you collect 100 fields, right? And then you're gonna be like 10,000 of subcolumns, and then you collect the metadata. The manifest file will grow. Yeah, for example, this is kind of one downside.
Right, because at ingestion time, you may not know enough about the workload patterns to know what to shred.
Yeah, that's true. Yeah, then probably, like as we just mentioned, when engine implements that, they may take some of the hints, right, to do, or maybe specify some rules or something. Yeah, unfortunately, like during write time, you don't have such kind of information otherwise. Yeah.
Thank you. Great talk.
Yeah, thank you.
So, Iowa, nice talk. Thank you for your introduction, Variant. So my question would be, can you provide, I know every user only use the feature, can you provide moderate timeline when the V3 spec will be finalized? And when the engine will support, is it Snowflake that has a timeline, or is it Trio has a timeline? Yeah.
Yeah, well, I think like Daniel like already kind of mentioned, it's kind of ongoing. You cannot give like a timeline for V3 or something, but
not even moderate timeline. I'm not asking you aggressive.
Yeah. But of course, like each engine, I guess, have its own timeline, I guess. Yeah, for example, Snowflake definitely have its own timeline, to deliver things. That's why we kind of actively work with community to push forward. Yeah.
So 2026?
Yeah, I guess probably. I mean, for Snowflake, I guess try to do something in this year. I guess. Yeah. That's true. Like, right. That's true.
My memory is column IDs are allocated globally and assigned globally. So that would mean that the shredded columns would have to be pre-decided, or you'd be like adding new column IDs as you go, and like you may run into like column ID exhaustion.
Yeah.
But the one nice benefit would be like when you're writing, you'd go look it up and be like, well, these have assigned column IDs, so therefore I should be shredding that way. But that doesn't really fit with what you described.
Yeah, go ahead. Oh, okay. Yeah, well, that's a good question. Yeah, actually, like for sub-columns, we will not have IDs. So what we do is gonna be have top column ID plus pass to have that. Yeah, so yeah, I think that's kind of like a valid question, right? So we will not have that.
Yeah, so the representation in Part A is that like for variant, there's the 2 columns. Those have field IDs, but then anything that's within the actual variant structure, they don't have global field IDs because each individual record can have a different representation. So yeah, there's no way to track that.
It's gonna be a lot.
Yeah.
Okay, thank you.
Yeah, thanks a lot.
All right, so now it's the favorite part of the day. We're going to take a 15-minute break and re-energize and come back. So now we're going to break it into 2 breakouts though. Breakout 1 is here and breakout 2 is in 2 conference rooms opposite here.
Thank you for your patience. Your event will return soon. Looking for caption support? Closed captions are available through the media player. We will be back shortly. Enjoy the background music as you wait for your event to return.
Start now. Okay, everybody, we're going to start the session now. And please take your seats, and we're going to start with, so this is, I want to introduce Andrew from Dremio. And the talk is about data-centric AI. And I think there was a question today about what about AI? When you talk about Iceberg. So this is a really good session. It's going to probably cover a lot of that, and maybe we can ask questions. Andrew, all yours. Take it away.
All right, welcome everyone. Please come in, take a seat. This is going to be a lightning session. We've only got 20 minutes together. So I love the conversation. It's going to be an interactive session, so please. All right, welcome, welcome. So please don't let me lecture you. Let's keep it conversational, keep it going. I've been on 9 planes this week, so if you can keep me awake, you'll be doing me a favor. You know, ask the hard questions. So my name is Andrew Madsen. I'm a developer advocate at Dremio. Before my life making TikToks for Dremio, I led data teams as VP of Analytics and AI at JP Morgan, Senior Director of Analytics and AI at ASU, a bunch of other stuff. On the side, I'm a professor of data science in a bunch of different grad programs. I'm an easy grader, so if you want your kids to get an A, put them in my class. Check. But most importantly, I just got my silver play button on YouTube. So now my wife has to introduce me as her influencer husband. We'll see how long that lasts. You know, it just started. She doesn't see me anyway because I'm always on the road. I did bring some stickers from Dremio, but who doesn't love free stuff? So please get yourself a copy of the Apache Iceberg, the Definitive Guide O'Reilly book. I think it's $70 on Amazon, so please get the free version. You'll be doing yourself a favor. We're writing another O'Reilly book right now in the Iceberg ecosystem to be coming out here in just a few months. What's Dremio? I promise this is the only slide. And then when my boss says, hey, did he say the word Dremio? You can say, yes, he did. And then we can move on with our lives. So Dremio, what is it? It's a data lakehouse platform. There's unified analytics, SQL query engine, full lakehouse management, autonomous data management, integrate sources, hybrid, on-prem, multi-cloud. That's Dremio. But what are we here to talk about today? I mean, a pretty esoteric topic. Nothing that ever comes up in the news at all. You know, DeepSeek, AI, what's going on? But we're also talking about Iceberg. I was in Washington, D.C. on Tuesday, meeting with a bunch of the heads of AI at some of the government institutions, and they were in on DeepSeek. They loved it. They're like, what's your opinion on DeepSeek? So I would love to hear your opinion on DeepSeek. But we're here to talk about Iceberg and where it fits in AI. Because AI is here, right? It reminds me a lot of the digital revolution from maybe 8 years ago, where that was really a kind of a top-down initiative. Us as data people, a lot of our time is spent bottoms up, saying, hey, here's these things that we really should work on, and then we're trying to get leadership buy-in. This, similar to digital transformation, is coming from top down. This is boards saying, hey, here's some money, go do it. This is AI. So according to Gartner, 75% of boards are making AI, quote unquote AI, one of their top 5 investments for 2026 at least, and top 3 for 2025. So what's the opportunity? So because it's coming top down, of course, there's business metrics assigned to this, right? They're looking for innovation, and there's going to be some metrics around like, what does innovation really mean? May mean something different in the business world than it does in tech world and for us. And at least 11 executives believe, more than half of the executives believe that productivity will increase by at least 11%. And we see that in the use cases. The Menlo Ventures just released a report in November of the top use cases for generative AI for the executives that they surveyed. Number 1 was copilots, coding copilots. I think we can see that across enterprises and mid-market, small companies, lots of coding copilots. Number 2, any guesses? What do you think the second largest use case of generative AI is? So we've got coding copilots as number 1, like by a far margin. What do you think? Call centers? It was top 5. It was close though. What do you think?
Chatbots?
Chatbots is number 3. Chatbots is number 3. What's the second one? Put your executive hats on. What do we care about? Money. So what is going to save us the most money? Automation. Automating processes, operations is number 2. And with the executives that I've been meeting with this year, I mean, what day is it? It's the 30th. I've spent 27 days in hotels talking to executives about AI. And I can confirm that these are their top priorities, like on the ground. So Menlo got this right. And they're expecting, of course, a bunch of revenue. But what is AI? So this is something that has come up a lot with meeting with the C-level data folks. They're saying, hey, my CEO, CIO is saying do AI, but they don't really know what AI is, right? Like we're old enough to remember when AI was deep learning, right? And it still is, but deep learning, neural networks, it's been around since, 50s really. But what's your definition of AI? If somebody came to you and said, hey, what's AI? What does that mean? Anybody want to be brave? What's AI? What's your elevator pitch on this is AI? Yeah.
Just software.
Just software? Okay. Is Salesforce AI? They want you to think so. What's AI? Anybody else got a good one? Do any of us know what AI is? Yeah, what's AI?
I can talk to a computer with natural language.
Okay, so natural language interaction.
NLP plus machine learning.
NLP and machine learning. Yeah, I like that. Any other definitions? Are we all kind of like, yeah, what's it?
It's like an algorithm that's just able to reason and generally capable.
Okay, so an algorithm, kind of like optimizing towards some objective with minimal human interaction, something like that? Intervention. Okay, awesome. So it's been around for a while, and when we see AI in the news, typically it's kind of talking about generative AI, because You know, we're like, oh, we can do neural networks. Like that's, we've been doing that for years. We can do your AI, you know, check the box. But when it comes to actually putting pedal to the metal and getting an AI system up and going, you know, it's great to focus on the models. And we're so good at that. You know, coming from data science background, we're really good at the CI/CD with models, watching model drift. We're really good at using Amazon SageMaker. That's right, we're at Amazon right now. Bonus point for me. So we're used to this with the continuous improvement with the models. What I'm seeing often is that we forget the data part, and that an AI system is the data and the model, and that the data also needs that same robust CI/CD care. And with that, because your AI training data needs to reflect the truth that the inference pipeline is going to experience. And if there's a truth gap between when the data is created and when it's curated, now we've got a problem, especially if there's big shifts in the reality, right? And we saw that. We've seen some machine learning and some AI mishaps that have resulted in some financial challenges for some companies. So we need to focus on the data as part of our AI strategy. And we've been in, if you've been in data longer than 5 minutes, this is the drumbeat we've been hitting for years, right? Like this is the same thing we've been saying about analytics, same thing we've been saying about machine learning, and now we're saying it about AI. But why is this different? Well, AI, if you're implementing generative AI, it does give you the opportunity to fail fast, but also fail immensely. So there can be vast consequences for a generative AI failure, especially if it's public facing. So Donald Knuth, the father of analysis algorithms, I think 1974, Turing Award winner. I love him. He's really great. But he says premature optimization is the root of all evil. And I think us as data folks, engineers, scientists, we love to optimize things. And sometimes it's focusing on that model. It's doing that feature selection. It's doing the fine tuning on the model or implementing our RAG, but we don't necessarily have our foundations in place with the data. So it can be premature. If our model is much more mature than our data, we could have an AI system failure. With ChatGPT, they're a great example of this, in my opinion. This is the brain trust here. It's safe circle, even though it's being broadcast, so I won't drop certain names when I tell bad stories. But so feel free to disagree. I don't have to be right all the time. But data was the competitive advantage, in my opinion, for ChatGPT. It drove their innovation. So for GPT-1, I never played with it, but I heard it was really bad, comparative to what's around now. 4.8 gigabytes of unfiltered data. What got us to GPT-2? 40 gigabytes of human filtered data. What got us to GPT-3? You know, we're almost to the turning point, GPT 3.5. 570 gigabytes of filtered data down from 45 terabytes of raw data. So really curated data. What got us to that big turning point, 3.5 and 4? That human labeling feedback loop, super high quality data. But what about the model? That's a transformer model. I'm not saying they didn't improve the model, but it's not a new innovation. They didn't create a new model. Reasoning, chain of thought, there's a case for that. But moving from 3 to 4, that wasn't model innovation per se, but that was an increase in data quality. Both scope and quality of the data helped get from ChatGPT 1 to ChatGPT 4. And so in that AI system, there's really model parity. If AI systems are our model and our data, there's model parity now, I would argue. Feel free to disagree. Remember, been on 9 planes, I could say crazy things. But we can API into all these models, right? Azure just put DeepSeek R1 into Azure Data Factory, right? So we can all use the same models. We're not, maybe we are inventing new models. Some of you look smart enough, you're inventing new models. But Hugging Face has, I don't even know how many models, so many models available. We all have the same models available, but data can be our competitive advantage. Because when you get those models, now we can distill information, we can fine tune, we could implement a RAG or a graph RAG on top of that, but it requires a strong data foundation. And we know that this is a challenge. We've seen analytics problems fails. We all hear that statistic, which I think could be made up, but we all hear it. 90% of analytics projects, machine learning projects, data projects fail. I don't know where that comes from, but I've heard it quoted many times, so it means it's probably fake. Anytime there's like a round number, it's like 70%, immediately I'm like, that's fake. But 72%, this comes from MIT in 2022, 72% of CIOs said that data problems were most likely to jeopardize AI ML. And I feel like that's true from just my experience trying to deploy AI and ML models. Data was often very challenging. Gartner agrees. Whether or not you agree with Gartner, yeah, we could talk about that. There's a case either way for that. But by 2026, they're saying they're projecting 60% of AI projects will fail overall, and 30% of AI projects will fail. Again, remember, round numbers, maybe made up. So 30% of those will fail specifically because of data quality. That's what Gartner's saying. So data quality is clearly a problem, especially for AI, especially for multimodal AI, right? Because when Bill Inman rolls out data warehouses, he's saying, we're going to create a central repository, right? This is late 80s, early 90s. Again, correct me if I'm wrong. I'm pretty sure. 87, right? He rolls it out. Nobody's correcting me? Okay. We'll roll with it. 87. He says this is going to be a central repository for all our data because we have these databases connected to applications, right? Pretty simple, structured data, awesome. He's saying let's consolidate these, have a central repository. We roll with that, but then different teams start building their own central repositories. Now we've got all these central repositories all over the enterprise. But he's saying the same thing for data lakes. He's like, it's an architectural pattern. He's like, there should be a central repository of data on your data lake. Let's call it a lake house. Really, in his opinion, and he's the boss, it could be called a warehouse, but we're calling it a lake house. Well, what's the challenge with this data? Silos. Like, who's ever seen a organization that's not a startup with no data silos? Anybody? No data silo problems? Okay. Somebody did tell me that they had one. I'm like, is it a startup? He's like, yeah, it's my company. I'm like, yeah, how many employees are there? 3? Yeah, there were. So anyway, data silos. It comes naturally. We acquire companies. There's growth. The tech stacks grow. We have different operating models. Sometimes silos happen, and sometimes they should happen. Sometimes there should be purposeful silos, but a lot of times they're just fragmented. It's not on purpose. It's got poor data quality. There's duplicate data. There's not a single source of truth. Doesn't necessarily have to be, but you have to know what the data is and why it's represented in the way that it is and where it is and which data that you should be using. There's a lack of metadata. There's a lack of governance, or there's too much governance? Can I say that? Access becomes a challenge. You have to, especially in heavily regulated industries, we have to manage governance, access control, data privacy. Here in California, we've got CCPA, CPRA, our global companies, we've got GDPR, the EU AI Act. We've got all these things, and then we've got our ethical responsibility beyond the letter of the law. But we have to be able to build things. We have to be able to be agile and flexible. We need to figure that out. Limited data access, insufficient metadata. We can end up stifling our stakeholders in data, marketing, risk, finance. We can become, instead of those fueling initiatives and providing the data, every organization says we're a data-driven organization, but when you actually look at the numbers, most are not. And sometimes we're the problem as data people. Sometimes, not always. Sometimes we're the problem because we can stifle innovation with bottlenecks. An example of what that can typically look like, let me know if this sounds familiar. So if you're a data scientist, AI engineer, data analyst, and you need to get some data, you don't happen to be a data engineer, what are you going to do? You're going to submit a request to your potentially central data engineering team through Jira. Don't get me started. So we're going to put that on we're going to send in a Jira ticket. They're going to throw it on the backlog because they don't know you and they're busy. By the time they get around to it, hopefully it's the right data. If it's not the right data for your AI ML analytics project, what do? You go back into Jira ticket hell. And then we start the cycle over. And central engineering's busy, you're busy, stakeholders are busy, everybody's busy, and the system just doesn't seem working. It's hard for the central data engineering team because of all those things we looked at: data silos, lack of access, lack of observability. So another buzzword, I don't want this to be hand wavy, but this is like your relaxing session of everybody else did lots of coding and now Andrew's gonna come and be fun. So data products. Data products can be a solution to this. Data products in general, there's different definitions of this. You know, different vendors happen to define them in ways that suit their product capabilities, which is fine. I get it. But the way I look at it, and everybody can have their own definition of data products, that's totally excellent. That helps the community. Data products should at least there should be some ownership, discoverability. If you have to be able to find the data, you should be able to, in some way, self-serve to get that data. It needs to be governed in some way, consumable, observable. It needs to be trustworthy. So when we discover the data, semantic search helps a lot. I'm seeing a lot of AI augment search capabilities for data exploration. The development cycle with data, we can learn so much from our software engineering counterparts with their rigorous process of the dev prod cycle, which Iceberg can help a lot with, but being able to develop views, to experiment, to iterate, and then to deploy, to get that into prod with a robust CI/CD process on the data side. Be able to have some kind of governance, whether that's centralized, federated. There can be decentralized governance, but I think it's pretty rare. I think it's more common to either have kind of a fabric approach where there's a strong, at least, security and governance layer, and then maybe federate out some of the ownership aspects. We need to be able to serve. Can we access this data product via API? Who can access it? How can they access it? When can they access it? What's their use case? And is it observable? Is there lineage? How do we handle incident management? How can we audit this? If you've been in product before, this is very similar to ownership, right? We need to own our data. Somebody needs to own our data. Is it the business? Is it you? It really depends on the organization. I've seen it work in a strongly centralized, a federated, a hub and spoke. I've never seen it fully decentralized, but I've seen federated leaning on decentralized. So done a lot of talking. I haven't said Iceberg more than like 3 times. So let's jump into Iceberg. So Iceberg, I mean, there's been so many great talks today. You know why Iceberg rules. Iceberg's awesome. We all love Iceberg. Open table format enables you to really integrate your data. That is one of the top problems or challenges that organizations have, regardless of size. Data integration, especially older organizations, banks, healthcare, they've got these legacy systems that are very hard to integrate data with, but they're also trying to move to the cloud, or they've got on-prem data gravity, and they want it to talk together, and then they've got some kind of janky Spark process to, loop it all together, and then the data engineers cry because it breaks all the time. But with Iceberg, having a data lakehouse as the core, I call this core and explore. The core of your data architecture, trying to migrate data, going Iceberg first if you can. Thinking, can we get this into Iceberg? Can we unify it? It doesn't necessarily have to physically move if it's in a data lake. It could be on-prem or maybe in a cloud or multi-cloud, whatever it is, whatever your architecture is. But that's the beauty and flexibility of Iceberg is if it's in a lake, you don't have to move it if the file format aligns with something you can put Iceberg into, Avro or Parquet. But not every use case. This is the challenge. This is where I've been meeting with lots of leaders, and they're like, well, Iceberg sounds great, but should we go all, they're looking for the simple solution of like, do this one thing and all your problems will go away. It doesn't work, right? Like Iceberg's not going to solve all of our problems. It solves a lot. We can minimize data silos for sure. It can help federate governance by integrating lots of our data sources together, getting that visibility, giving us that hidden partitioning, the schema evolution, the modular approach to being able to choose your different query engines, your different catalogs. The Iceberg REST catalog specification is awesome, but it's not the solution for everything. So how does that work? If you can have a core of your data lakehouse Iceberg approach, then in a data fit for purpose approach, you're able to then branch out as needed. Sometimes you do need a time series database for your sensor data, and you need specific time series functions that aren't available in Iceberg right now. That's fine, but we know why it's there. We don't have this massive data estate that's ungovernable. If we can consolidate and we go lakehouse first and then branch out as use cases are needed, then we are able to not have tons of different copies of our data. We're able to have more observability, control, flexibility to adapt our operating model to our needs. Vector databases, solid use case, not in most, right? You can't do vector in Iceberg, right? I know single store supports the Iceberg data type, but if you want to move to a vector database, you're probably not doing that on your lakehouse, right? So you need to core and explore. And I've seen that work a lot because now we're shrinking our data estate. We're controlling for costs. We're keeping our FinOps manager happy. And we're able to, one, manage our analytics and our core workflows, the things that's keeping our decisions running. And we're keeping our governance tight because now we can see all of our critical data. And we're able to expand and be flexible as needed by going into a graph database, a vector database, a time series database as needed, and we know where it is. So then manage your core analytics workflows while developing and deploying AI. So this is what it could, here's what a lakehouse could look like in practice. And this is a marketecture slide, so you can tell a marketing person put this together. But essentially, like Iceberg's awesome because you're able to really, whether it's on-prem, in the cloud, we can use Iceberg, right? Iceberg is amazing. I'm a huge fan and super happy that it's here and with all the huge contributions from so many different people and companies. But with the top-down push of, hey, do AI, like do all the other stuff you're already doing, that's awesome, but also do AI on top of that. Here's a strategy that you can, or a mindset that you can come forward with of how can I keep managing the core of my data operations? Should I adapt my operating model? And how can I strategically branch out into AI and ensure that I'm both maintaining my core, but driving that explore motion as well? I think data products are a strong part of that, but again, I don't want it to be hand wavy, like just dropping buzzwords. But data products is essentially bringing accountability and visibility and ownership to specific data that should be fit for purpose to drive specific business outcomes. All right, so thank you so much. This is a lightning session, so we had to really fly through that. But I really appreciate your time here. Please follow up with me with any questions afterwards. And of course, please get a free copy of the Iceberg Guide. Thank you so much.
Thank you, Andrew. Up next, we got Victor. And Victor, just trying to make sure we got your session description. All right, so we're gonna talk about the Rust implementation. Oh, let's go over there. I think we're gonna. Oh, is this yours? No. Okay, so there. You can bring yours too, or.
You guys soon. In March, so I'll let you know. That's good. All right,
All right. So when while Victor's setting it up, Victor comes from Germany, Munich, and we've actually met a few times here in San Francisco. And Christian, you're here too. They're co-founders of Lakekeeper. This is a Rust-based implementation of the Iceberg catalog. Really unique, very interesting. Take a look. Ask very, very tough questions, because every question we asked Christian, he had a very good answer for it, and he went into a lot of detail. So I want to see, where is that edge where we can stump you? So certainly we would love a lot of engagement as well. All right.
Okay, thanks, Tesh. And well, I do have a slight different presentation. It's less on Iceberg, Rust. And we have here. Just give me a sec. Can you help?
Yes.
Perfect. Yeah, so I prepared a little bit different type of presentation today about the actionable metadata. Well, first of all, thank you for participation. And I know sometimes it's hard to choose between parallel session, and there's like a parallel sessions here as well. So I appreciate your participation, and thanks for picking this session. Well, let's just have a conversation and about something that might change your understanding about the metadata. And that is something what makes metadata actionable. Well, first of all, open source. And I kind of found the session from then today in the morning about the open source, about the collaboration, very, very inspiring. And I would like just to start with acknowledgement of open source. And that open source and Apache Iceberg is a reason why we're all here today, right? So the community is possible because of open source. Open source drives innovation. Open source is a collaboration for all of us. And look just at me yesterday, just arrived from Germany, and right now I'm able just to speak in front of you and present Lakekeeper, present the actionable metadata. And maybe just before jumping into the session, for me to understand, can I just ask you to raise a hand who use open source in your daily job or privately, just to understand like how it's adopted? Okay, there are a few of you. And maybe now kind of a tricky question, who of you has contributed to open source? Okay, so less hands than like as a users. But the good thing is about the contribution, guys, it's not just writing code. Contribution is maybe just to test something, to file the issue, find the bug, or maybe just to improve documentation. Or maybe just, you know, like you have a specific issue on your daily job, and you just will go to the project and you will open the issue for that. The simple way to contribute is to start a project, to drive the adoption for that project. So what I would like to introduce is Lakekeeper. Lakekeeper is an open source project. It's a REST catalog for Apache Iceberg tables. Lakekeeper is, as Tesh just mentioned, written in Rust, and it's licensed at the Apache 2.0 license. And you know, like the idea is about the contribution, as I said, and here's a QR code, so you can just scan and start a project. And when you're gonna leave the session, you can actually say that you are contributor to the open source. Well, I'm Victor. I'm creator of Lakekeeper. I'm co-founder of Acamo, and if you have like any questions later on, just reach out to me. He's email, LinkedIn, or I'm gonna be here around as well. The metadata and data. So what is actually the status quo if you look at the situation right now? So data has been for past 15, 20, 30 years in a spotlight, on a main stage. So all the time businesses act on data. You know, like customer was on a website, let's send him an email. Customer opened the email, yeah, let's give him a discount, and so on and so on. But what about the metadata? Metadata was kind of a necessity. Like, okay, we need to document the metadata. I need to open the wiki page and put inside of a wiki page who is the owner of that data. And no one really took care. And even like Andreas, you just described, like that was a missing part. We don't really know about the data itself because we don't have a metadata. And at the same time, like businesses act on data, but the businesses complains about the data quality, missing data profiling, maybe outdated results, there is no really data ownership, and so on, which is actually part of a metadata and not of the data itself. And in that situation, where we have like the problem and challenges, but the metadata stuck somewhere in the past as a documentation. And the question is like, how did we get here actually? And look at the journey of the metadata. If you look like 1980s and like 80s, 90s, where we had a data warehouse as a single monolithic system where we stored all the data, maybe like a Postgres database or like any database where metadata is mostly like an information schema where you store your tables, use stored procedures. Monolithic, bureaucratic, very strict, rigid, that gave a structure for us. But at least if you look at the agility, it was really hard to scale your processes around that. And I know from my experience that companies had maybe twice a year an upgrade of their tables or on a data model. Okay, so we said let's solve that problem and be more flexible, and we got the data lakes. At the beginning, maybe on HDFS, and later we got object storages, and we could actually be more flexible here. The main actor was Hive Metastore, which put kind of a facade as a table in front of files, and you could store like Parquet, CSV, JSON, and for the client it was, oh look, that's a table, so I can just play around that table, I can select that table. But at the end, Hive was not delivering the expectation what we had from a database. So it kind of failed maybe. Today, we have a lakehouse with open table formats. And so open table formats, Apache Iceberg, made a promise that we can combine structure from a data warehouses and flexibility from data lakes. That was the promise given by Apache Iceberg or like by open table formats. And the main role here plays actually a REST catalog, because REST catalog manages the metadata. And if you look at that on very simplified architecture of that REST catalog, what you have, like, okay, we have a data which we store somewhere in an object storage. So we have our Parquet or C, Afros, it's all known, it's all good. But if you look at the metadata right now we have a new component which is in charge of lifecycle of a metadata. Or maybe it's even in charge of maintaining the table itself. So you can just go and read the table. And as well, you can just manage the access of that table. The question is, still, is that what we gonna stop here? Because that kind of like the first thing what we need to solve with structure and flexibility, or are we going to use that metadata for something else? Because still the ownership and governance is not solved through a simple REST catalog as is. And what we have right now in discussion with some companies and some design partners is like, actually to solve the problem of data governance, of data ownership is in metadata, but only if metadata is actionable. And the question is like, what is the actionable metadata? Well, it's maybe kind of self-explanatory, like you have your data, which is not just used for a documentation purposes, but that data is able to trigger a process by itself. So, and that process and that recipient of that process might be a human, it might be an AI, RAG application, or something else. And the very crucial part of that is that we have a relationship between data producers and data consumers in that situation, where metadata, through the action, can enforce the relationship, can describe the relationship. And why do we do that? Because we need stable collaboration and sharing between analytics, between AI. And the question is, what actually has changed in a couple of last years that we have that challenge right now? And the changes, not just on the technical side, that right now we don't have like a single database in a monolithic approach anymore. What we have a decentralization on organization level, and we have decentralization on the process level. So which means if you go to any mid-size or big company, you will find that every unit is right now independent. Like something what we called yesterday a data silo, and everyone was trying to fight the data silo or like break the silos. Right now we call it a data domain. And suddenly data domains are positive, data silos are negative. But the question is, if everyone is independent in a self-service mode, producing data products, how are we going to cope with that situation? Because there is no single place where you have role-based access control to manage the whole thing. And the answer is what we see right now exactly in a metadata, where we can actually deploy and implement the actionability to enforce the relationships. So how we do that in Lakekeeper? And in Lakekeeper, we have some specific implementation, which we call change events. And because Lakekeeper is a REST catalog and it's positioned a pretty interesting place in a center of like the lakehouse architecture, but it's still independent. So what do we have? We have a compute. Let's say it's a compute which runs an alter table operation. And usually that's some operation which will run through the catalog and it's done. But what we can do, Lakekeeper, we can emit that to a queue, that change event, and we can make the reactivity on every metadata change within a catalog. So in that situation, you can imagine that some process will listen to a queue and actually react on that. And the question is right now, okay, we have that in place. So how can we solve something, what I was referring before, like we have all that data domains, and we need somehow to govern the data domains. And the conceptual answer is computational governance. So how can we do the computational governance based on the change events? So let's imagine we have a data engineer, which is from a domain, data domain marketing, and that domain is responsible for the customer data, customer metadata for some orders of customers and so on. And so what we have as well as a domain from a sales, and there is a data analyst who actually builds a reporting on top of that data or data products from marketing. And that data or that report, that numbers goes to a management. There is a business process which needs that data to make a decision. And with that decision, they're going to make investments, or they're going to make a decision to cut costs and so on and so forth. But today, our data engineer had a great idea to make some changes. Just run an alter table. And that was, let's say, in the morning, that person got inside the organization. And because the data engineer has role-based access control as administrator, that person can do that change, which means for analysts, reports are broken. So no of that reports are able to run anymore. And that is not just a technical issue in that situation, but it's in the business impact for everyone on the management side, because they're not able to make a decision anymore. Well, that's something what is not solved today from a perspective of a classical lakehouse. But if we can just apply the computational governance principle with a Lakekeeper and change events, what we can do, we can emit that event to a third party, a data contract engine, which has a contract with actionable SLOs. And the SLO is like some different type of objectives. And one of them is a stable schema, which means in the moment when operation alter table runs, the event goes to the data contract engine, checks the contract, like do we have some service level objectives here? And one is like stable schema. So you're not actually allowed to do that, even though you are an administrator of a table. So what data contract engine will then send back to the data engineer is a conflict message, which means right now what we have two different concepts. One is a role-based access control. From a classical perspective, I can do everything, but the other one is a business constraint as a stable schema, what is expected by a data analyst in that case. As a next step, the system can actually inform both of them, like engineer and an analyst, that something has changed or is about to change. And data engineer can actually go to the analyst and churn the contract and tell to the data analyst, well, you have now a grace period, let's say 7 days, to adjust your reports because I need to make that change. So that is one of the examples how actionable metadata can make the whole situation controllable, or as Christian, my co-founder, says, to make an unbreakable lakehouse, because all that consumption pipelines right now in that situation are not breakable. And this is a major problem in many organizations. And you can just imagine if it's like a huge company where you have this process as a value chain where someone relies on other numbers. And always is interesting to have a conversation with support personnel who needs just to go and understand where exactly is a breaking change that needs to be fixed. In a discussion with the companies right now, like with this feature, what we can achieve additionally is not just a schema changes that can be prevented upfront, but we can just look at the statistics. And like in presentation before, we have all that AI components. And the statistics is quite interesting because if you have a metadata change, it might have an implication of some AI training model which needs to be rerun, not just because data has changed, but because the metadata has changed. So I just would like to give you like a future outlook on what can be done with actionable metadata. Well, the interesting part is about the analytics and AI silos, let's put it that way. So they are kind of not very connected. So if you go to the companies and you will have a conversation, you will probably find that data engineering don't talk much to the data science. But they share the same data. They share maybe even same business goal to increase revenue or maybe just to cut some costs and so on. And the thing is that we have a unique way to connect both data engineers and data science through the metadata, because the same reason, like if you have a data silo for data engineer and you have a data silo for a data analyst and data silo maybe for scientists, now they can go and sign a contract and explain why they use this data for what type of purposes and what is actually happening if data is going to break their pipelines. The next use case is the lineage between business and technical pipelines or technical information. Right now, you can just find a lot of solutions where you have a technical lineage. You have like table A, and then you have the ETL process, and then you have like a table B, which is a result. And in my conversation, that situation, like, okay, what is the business process that causes that data at all? What's the business process that produced that ETL process? And what is the business step that is going to be triggered by that new data? And there is no information, so we just miss that link. You know, like it's comparable, like if you go back to your school days and you have like your math task, and you just need to run the calculation, and then you write at the end of your equation like number 42, the teacher usually asks like, how did you get to that result? And that is some type of information what we miss in this situation as well. So that information resides in some business processes. We have some activity diagrams, we have some business process model notation, where exactly this information is kind of stored, but it's disconnected from a technical village. The next point is the automation. I mean, that is something what we expect to get pretty soon in our AI agents in operation. I spent 2 days here in the Bay Area, and I see a lot of billboards, AI agent, operator, kind of interesting, like to have a billboard and which talks about the digital world, but still cool. And I see the same type of development that's in 3-5 years, the use case what I was describing before with data analyst and data engineer. There's going to be like no humans maybe anymore in that situation. There are going to be a lot of AI agents, and those AI agents, they need an automated way how to negotiate a contract, how to define the SLO on some specific stuff. There is no way anymore, like maybe as today, that someone is called someone and asks about the data, like, can you give me the data by tomorrow? And the person will tell you probably, oh, let's just postpone it for a couple of days. But exactly through the actionable metadata, I can achieve a very high level of automation. And maybe just the last one is the sharing and secure sharing for the data contracts. In most of the cases and most of discussions inside of the companies, what I see is the concentration on itself, on its one company, and like, okay, are we going to be a data-driven company, and what do we need to achieve that? But if you're going to zoom it out a little bit, and you will see like you have a data-driven economy, you have a supply chains. Let's just take an example, automotive, pharmaceutical, all the different supply chains. And all that single companies in that supply chain is a data silo more or less. And all of them need the information, and maybe even like the information needs to be flowed back from a manufacturer to the supplier to improve processes, to find the new products, to get like the most needed information. And that is only possible if suppliers between them have a contract, which will actually ensure that data shape is informed, that the metadata is informed. And in parallel, what we have a lakehouse, which gives us a way to share the data between different companies without making a copy. So here is exactly the way where we can just combine the metadata and data and make it both actionable, which will give us like the easier way just to become a data-driven economy, not just a data-driven company. Well, that's it from my side. I will just thank you for your attention, and if there are any questions, or maybe afterwards, I don't know how it's planned.
Any questions right now?
Yeah.
Hey, Victor, thanks. I'm really curious, when you guys first started, what was the Iceberg REST catalog ecosystem like? And what was like the first problem you guys wanted to tackle? And then how did that evolve over time? What are the main problems that you feel like the Iceberg REST catalogs should be solving?
Yeah, so when we actually started, we had mostly like tabular as a service, and that was kind of the idea that we need just to build something on our own because we need to run it in our own environment. And we started to build a catalog because we needed a solution that can integrate with data contracts and actually provide the data mesh principles. That was the whole idea about writing our own catalog.
Cool, thank you.
Perfect, thank you. Yes. Oh.
Am I super simplifying this by comparing it to like a feature on the data observability part? For instance, like reacting to a pipeline is something given like most of the data observability platforms does as well, right? Like including like chains of creating policies so that they try to prevent it or just trigger some events based on it. is it on the same lines? And if so, like, is there a hard dependency on Iceberg? Is it just because of the metadata offering that it is built, it's reasoning on Iceberg?
Well, the observability will give you maybe what I call a post-mortem message. Your table is broken, and red lamp will go on, and then you just go and find what exactly was broken.
Yeah, something like a reactive is what happens.
Yeah, and with having Iceberg REST catalog, it gives us actually a preventive mechanism to be more in control. That's something what is not possible if you have like observability will connect to the Postgres table and someone will change the Postgres table and then you need just to find a solution. Here we can be preventive, we can just define the relationship, and that is possible with Iceberg REST catalog because it's decoupled from the technology. So it's a decentralized and distributed way of handling the information. So it's possible with Iceberg REST to be preventive. On observability, it's possible, but it's more like post-mortem when the change is already in place.
So here, should I understand this like before the commit happens or before the transaction
Yes.
on the table happened, we just check it at that point in time and then never allow the commits to happen at the first place?
Yeah, absolutely. And you can just define all the different SLOs. It can be stable schema. It can be that you have a specific quality target that you just want to expect before pushing the data inside. So all profiling information, statistics, there are a lot of stuff which is around the table and around the data itself. Yeah.
And the second part of it where you mentioned the future outlook towards both the business catalog and the technical lineage plus the verbs of the data contracts. Is it like somewhere getting into the line of the Calibra world of?
No, not the business catalogs. I'm referring more to the business processes. So like if you look at the business, they don't know about the catalogs at all. What business operates with is a business process model notation, so BPMN 2.0. That's a different type of a thing. And in that business process, you will define like the start of a process, what is happening within then, what type of decisions you need to make, and so on and so forth. And that is something what is actually drives the whole data thing. So without that business, there is no data at all. There is no data sitting somewhere. So someone needs to do the business, someone needs to go and sell or produce, deliver. And if that happens, then we have the data inside of a database or inside of Lakehouse. And that is exactly missing link. Right now, if you will just open your Lakehouse and you will find a table, ask someone, why do we have that table? What process actually causes that table? Or what process will be triggered if we're going to change anything in that table? What will break?
Thank you.
Yeah. Thank you.
All right. Okay, thank you. We have, thank you, Victor. Really appreciate it. So we have dinner outside, and we are the only ones left who have not had the chance to grab a bite. So thank you again, everyone.
Enjoy.
We're gonna take a break for an hour. Now, along with dinner, we also opened up drinks on where the swags were, like against the wall. So feel free to pick up a drink now or later, but everything is open at this point. We will come back in 1 hour. Okay, thank you.
Your event will return shortly. Please stay tuned.
We will be joined. We will give back to the people to make so. And we will enjoy the ocean space.
Enjoying the music? All content you're currently listening to was produced by Amazon's Audio Studios team. Stay tuned for your scheduled event. Want to host your own event? Create your meeting experience today at meetings.amazon.com. Thank you for your patience. Your event will return soon. Looking for caption support? Closed captions are available through the media player. We will be back shortly. Enjoy the background music as you wait for your event to return. Your event will return shortly. Please stay tuned. Enjoying the music? All content you're currently listening to was produced by Amazon's Audio Studios team. Stay tuned for your scheduled event. Want to host your own event? Create your meeting experience today at meetings.amazon.com. Thank you for your patience. Your event will return soon. Looking for caption support? Closed captions are available through the media player. We will be back shortly. Enjoy the background music as you wait for your event to return.
Because usually the metadata parsing is done just in the query planner. It's like a single, it's like a single node. So if think about it, if there are many manifest files are out there, so it should be take a very long time for the query planner to just parse and decoding those manifest files. So it could be the bottleneck. So what StarRocks do is StarRocks translates the metadata parsing job into a regular execution plan. It makes to a normal SQL, something like that. So every BEs in the systems can read and parse manifest files parallelly. By doing that, we can fully utilize the backend nodes and to avoid the BE to the bottleneck. While the latency could be reduced down to a fraction of number of BE nodes. So we fully utilize the resources. The second problem, the second challenge I mentioned is that handling position the equality delete files could be inefficient because in traditional ways, deleted files could be read and parsed multiple times by different BEs, executor. And scan operators could have a very complex implementation inside. So what StarRocks is to, again, it translates the handling delete file job into a regular query execution. Like you can see from the diagram, we add by using the left anti-join and the union all join nodes, how to do that. To handle the position delete files, we add a left anti-join node with join predicate or predicate like on their file name plus position. And to handle the equality delete files, we add a left anti-join. The predicate on that is sequence number and the primary columns. And finally, we union data files without any delete files. That's it. So you can see it's just a regular sequels. Okay. So the result is that delete files are only read and parsed only once, and scan operators just have a simpler implementation. Meanwhile, we leverage the StarRocks efficient join algorithms. And the third challenge is that dispatching the files could be in a blocking way. So because dispatching files could be in a blocking way that BE, the backend executor, has to wait until the FE planner dispatch all files down to it. So before the FE collecting all files, the backend has to wait. All backends has to wait. It's a waste. It's a huge waste of resources. So what StarRocks do is the StarRocks dispatch file in small batch, like the FE, after FE just collecting a small batch of files, FE just dispatched files down to the FE. So as a batch of files being dispatched to BE can execute instantly. But meanwhile, the FE can keep collecting the file, the data and the delete files. So you can see that the FE and the BEs can, work in a pipeline way. So the result is for some for common queries, the latency could be reduced down to 10 or 30%, but for some special query like previewing the data, like select star from T limit 10, the latency could be reduced more than 50% or even more, yeah. So that is the general optimizations. We have some, besides that, we have some other features and optimization that could make the StarRox be a better lakehouse engine. I just want to list a few. The first one is data and metadata cache. So we can save the I/O costs from the repeatedly fetching the data from the external storage, even that data has been fetched before. And MPP memory data shuffling, it's just so the data exchanged between different nodes don't need be put on the disk like Hadoop does. It's way inefficient. And StarRox is written in C++, so we can fully utilize the SIMD instruction set. And finally, I want to mention the materialized query rewrite. Because of that, customers can use materialized views seamlessly without manually changing any SQL at all. And you have to remember that the customer side usually have a very, very long, complicated SQLs. And after you want, and nobody want to change that. Nobody want to touch that. And since we have materialized view query rewrite, just to create materialized views, boom. We just rewrite it. We just use the materialized views directly. No change in SQL at all. Yeah, so that's basically about StarRox. So finally, I want to share a real-world use case. Here is the red node. It's also called Xiaohongshu. I guess it's probably you already know that because of recent events. Right, yes, okay. It's a social media company with 200 million plus monthly active users. Before they move the lakehouse workloads to the StarRox, they already employ a real-time StarRox cluster. And that cluster, there are 100 million rows ingested per day, and there are 30,000 CPU cores. Average latency could be down to 20 milliseconds. So StarRox has a very good reputation inside the Red Node team, and they trust us. And once they want to move the lakehouse workloads to other place instead of the Presto, they think about if we can move the workloads to the StarRox. So they were using the Presto. The scale on the to query the Iceberg and the Hive table. The scale of data on Iceberg table is EB level, and there are 10,000 tables. The challenge with Presto is that they have to maintain the StarRox and the Presto. It's quite annoying, high maintenance. And they were not satisfied with the performance of Presto in terms of latency and concurrency, while they have a concern about high availability of Presto. And they replaced the Presto with StarRox, and you see StarRox can directly query the Iceberg and Hive table. And if customers are not satisfied with the performance, okay, good, you create materialized views. Remember, we have a materialized views rewrite mechanism, so no need to change any SQL at all. Just query get performance get boost, transparently. So the result is that query sees average of 6 and 7 performance boost, P90% decreased by 90%, and only have to maintain StarRox, this stack. And the good thing is that since StarRox can be compatible with the Presto and the Trino dialect, So the customer side don't need to change because they were using this Pretzel SQL. They don't need to change the SQL at all. So it's they have a very, very fast migration process. So that's the case of Red Note. Okay, thank you. That's all. Thank you very much.
Starbucks at this point, but what was historically challenging for us is basically the Iceberg API does not provide you kind of good enough tools for like fetching updates, right? So unless new partition is created, you have no idea that old partitions were updated. So technically, when you referencing to the basically materialized view magic, right? So that is not a good suit for Iceberg unless you're doing append only and only appending the new partition. And basically there's a trade-off, right? So if you're caching metadata, then you have no way understanding what are the new things that were there. So what are you folks doing to solve that? Thank you. I'm sorry?
What's the problem? I don't catch up.
So, I mean, is there any improvements that you do on top of the Iceberg API that allows you to get updates faster? Because as I said, right, so unless Iceberg creates new partition, any AMVs that we create on top of that, they won't see that.
We create, you mean the materialized views? Materialized views, we create materialized views based on partition levels, refresh. That so if Iceberg partitions is updated, we have to materialize this partition materialized views has to be refreshed to caught up.
So you're saying that like the mapping of AMV partitions to Iceberg partitions would actually watch the partition update?
Yeah.
And like if it's a merge and read, it also watches it at this point?
Yes, partition levels catch up.
Okay, so but that won't work with metadata caching?
What kind of caching? Sorry.
So you mentioned the basically that
Metadata
you're
caching.
unpacking Avro, manifest, and so on, right? So, and the way to streamline and improve that, you folks are putting caching into it, right? So basically, if you cache it, then technically you won't be able to.
We catch the manifest file instead of when we pass the metadata, we just catch the manifest files to avoid
Yeah, but I mean, like, boom, I created another snapshot and another manifest files are in. So what to do in this case?
Yeah. Yes, we will, yeah.
So basically, and this is done by like monitoring Iceberg
Background.
snapshots?
Yes, background, yeah. We
Okay.
have a background process to do the partition refresher to keep comparing what is the latest what is the latest snapshot of a partition update time compared with our materialized views update time.
Okay, I see. Yeah, that might work. Let me test it, and I'm gonna back to your GitHub. Thank you.
Okay. I also like the chain block stance that basically it's a relatively near model that allows you to reconstruct the chain block on command. You can actually, I mean, in Iceberg, even pages represent feeding insert, so by default you will get
Yeah, I see. I mean, like just for my in-house product, right? I want to rely on the tooling that I use, which is Starbucks in this case. So I'm sort of waiting patiently until this can be pulled in. Otherwise, like AMVs on top of Iceberg been, let's say, problematic. As usual, trade-offs, 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 right? So either you're pulling, updating, or you're giving this blazingly fast performance of AMVs on top of Iceberg, say. Thank you.
How many QPAs can each vCPU handle with Starox? Yeah. What is the max performance you've seen?
I don't know if it totally depends on your customer scenarios, right?
Like on an average, what? I'm just curious to see
Average
like the
QPS,
concurrency.
average QPS.
Sorry?
Average, you mean average QPS?
Yeah.
I don't know, maybe for simpler, okay, for simpler query, point queries, like you can, well, like 100 or 100 nodes, you can probably sustain to 100,000, 10 or 10,000 maybe QPS, I guess. We have those customers, but if you have a very complex queries, then QPS won't be not high. It totally depends. I
Okay.
won't say
Depends
a
on the
exact number.
queries is what you're trying to say.
Yeah.
Okay.
Okay.
Thank you.
Okay. So did you implement Iceberg in C++, the spec?
No.
You use Java?
We use we kind of read the bucket files in C++, but we kind of doing the metadata parsing sort of stuff at FE using the Java, using this C++ or Iceberg Java SDK, but we don't use. No, we don't use the JVM. But okay, for the query, actual query the data, we use the C++ to the parse the packet files directly. But for I've mentioned there's a distributed metadata parsing, because that parsing could be very complicated. So we use the Java JNI to call the Java at that part. But for the normal queries, we don't we directly parsing the packet files in C++. Yeah.
When you do distributed planning, and then how do you pack manifest so that you utilize the compute as much as possible?
Yeah.
Because what would happen is that in one manifest, you end up scanning only one file, but on the other, you end up scanning 2 or 3 files. How do you efficiently bin pack before distributing those manifests?
Yes, we have a kind of auto mechanism to decide if this manifest files is large enough to be distributed, but it's quite detailed. It's written by, okay, actually it's written by another guy. Yeah.
Okay.
There is a heuristic, yeah.
Right. Thank you, Jan. This is wonderful. We appreciate the talk. All right. Up next is Akash Cloud. Sorry, Karthik, right? All right. Wonderful. This is a really amazing session. It talks about speed at 4 times the lower cost. So, a lot for us to look forward to. Yep, sounds good.
Good evening, everybody. I'm Karthik Kulkarni. I'm a co-founder of Akash X, and we are building what we call storage accelerated lakehouse engine. So storage acceleration is a technical approach that we are taking to improve the cost performance when you run SQL workloads on your data warehouses and lakehouses, and I'll talk about that. Uh, but at the very high level, we see that a lot of innovation has happened on top of S3, right? It has assumed that S3 is going to be the state of art forever. And a lot of innovation would happen mostly on the compute side, but basically because everybody has simply sort of assumed that we will build on top of S3, storage itself, a lot of evolution that could have happened, in my personal opinion, has not happened, and then we are, that's why we're taking this radical approach of diving into the storage side rather than the compute side. And today I want to share with you some of that approach and our learnings on how Iceberg and in general SQL workloads can be significantly accelerated if the innovation actually touches the storage side. So before that, just a little bit background about me. I have spent over a decade building databases. I used to lead an important team at Oracle called Transactions team. So my team was responsible for a lot of things ACID within the database. And my co-founders, Darshan, was actually head of data for a couple of unicorn e-commerce companies, and also Chris, who was the chief business officer at Minayo. So before I dive in, quick thanks to some of our investors and advisors, Sam from MIT and David Devitt, famously or infamously known for the Devitt's Clause, and also some of the investors that have backed us. So open table formats have clearly arrived, right? People hate proprietary internal formats for various reasons, including the not having vendor lock-in, or also because a lot of data integration and innovation can happen when the data is unlocked and unchained and free, right? So, and Iceberg seems to be taking the lead, at least because we are in this particular meetup. But my observation is that the engines are really headed for the iceberg. There's a Titanic reference here, if you couldn't catch. So what I mean by that is, when you look at the evolution of the databases and the database engines, there are decades of optimizations that have evolved over the time, right? And a lot of these optimizations, at least in databases technologies that were built over the past, have relied on either the internal storage formats or the internal storage engines. Now, if you ask them or put them in a situation where, hey, there's this brand new open table format, and by the way, it doesn't live on your storage engine, it lives on some other storage engine, and you got to run on that. What happens is that the existing engines, developers are trying to evolve their engines to obviously make it work on these new open table formats on this disaggregated storage layer. But those optimizations that relied on the internal formats and internal storage engines have somehow been lost. A lot of optimizations around exploiting the data locality, around co-location of data with certain compute, all of that is somehow not applicable in this new world, right? And there is a consequence to that. The consequence is you are paying in terms of cost performance. If you take any engine today and benchmark it against its own internal storage engine or format, and then make it work on, let's say, Iceberg, I don't think you'll get the same performance. This is not to say that Iceberg lacks in terms of its ability to support the engines to have unleash their optimizations, but it's just that balancing compatibility and performance on a new turf becomes a challenge for these engines, right? And also this direction itself is sort of as people refer to is unbundling the database as such, right? I come from this OLTP world where a database actually did a lot of things, or mostly everything. Right from storing your data, indexing, like querying, any housekeeping activity that you had to do, like compaction, everything was basically done on a database, and you just use SQL to run on top of it. Now, you see there is this storage layer that's separated. There is this open table format data that lives. There's a different catalog. Then there is an engine, and to ingest there is another engine. To query there is another engine. So what happens is that when you have so many tools, and you're unbundling the whole database, a lot of your housekeeping activity, for example, gets sidelined, and that's why you had these Spark packages people used to run to compact the data, and now that has led to this S3 tables, I believe. So when you have this unbundled system and you package together different components, modularize and then build something, it's hard to make it a well-oiled machine, which databases used to be in the past, right? And it all adds up, right? And if you look deeper into the root cause as to why and how we came here, I'm not necessarily saying that this is a bad situation. There are a lot of advantages to this unbundled ecosystem. I would say a lot of cost and performance issues of this era dates back to the whole compute storage separation itself. Back in the day, when Amazon said that S3 is going to be the layer where you keep all your data, and then you run OLAP engines or whatever it is for that matter on top of it, what happened was you made access to your data 1,000 times slower compared to a world where storage and compute were tightly coupled, right? And there is definitely a big advantage to it in the sense that you could evolve different layers independently, but you're also going to pay in terms of cost and performance. So what do today's OLAP engines do, like the one we heard before? You parallelize access to the data, right? To overcome the challenges of both latency and throughput. You parallelize and then have many different cores. You either do that or you also resort to aggressive caching, right? Now, interesting thing about OLAP is that the working set itself is not very defined, and the query patterns are random, and you could end up having a huge working set. So if you rely on aggressive caching, your caching could actually be, your cache could be pretty huge. And your caching, remember, on these highly parallel machines, big beefy machines, compute machines, because you have to parallelize access to the storage. And not to forget, these compute machines are ephemeral. You lose them, then you have to recache, right? So all of these things add up, and the result is that your cost performance when running on data lakehouses is not the greatest, at least when compared to the previous days, right? So what we are doing is taking a slightly different approach. We call this as empowered storage architecture. We have a storage accelerated layer. We call this as ES3, as opposed to just S3. And empowered storage, the philosophy is that you swing the pendulum a little bit backwards. We went from tightly coupled storage and compute to a fully decoupled, disaggregated storage and compute, and we come back a little bit. We add a little bit more compute to the storage layer, and the storage layer is now capable of doing certain operations that are data reducing in nature and consume less compute, so that the fetch from the storage is not too much to overcome the latency, to overcome the throughput issues, to overcome the need for significant aggressive caching on your compute layer. So what ES3 is able to do is it is able to do partial filtering, simple partial aggregations, and certain data reducing operations, like, for example, look up the metadata and then access the data, which sometimes has to be done over the network. Now you push it down to the disaggregated storage layer and so forth. So the goal here is to reduce the data fetch dramatically when you access data over the disaggregated storage layer. And in doing so, the memory footprint would be lower in the compute side, the network utilization would be lower, and in general, you would need the smaller instances to execute the same or similar workloads. So that's the direction that we're taking. Now, ES3 itself can work as a fully, what do I say, autonomous storage layer, or it can layer on top of your S3 and serve as a red hot tier, for accelerating analytics workloads. S3 itself has many tiers. Think of this as an extension layer, or tier rather, on your S3 if you're using it in a lakehouse mode. So zooming out a little bit, this is not new at all, right? Like, pushing compute closer to the data has always been, ancient wisdom in the database community, right? If you see most databases, they do push down of various operations within their own stack. If you look at Netezza, that was one of the first ones to push partial SQL down to the hard drives using FPGAs attached. Oracle Exadata, the team where I work for, we push SQL down to the file system level. And you can think of Hadoop as basically map reduce compute pushed down to HDFS storage nodes. So what we are trying to do a little bit different is that we're pushing down partial SQL down to a disaggregated object storage. And this is relevant in today's world because when we talk about storage, people think of object storage. And this is especially important in the era of open table formats like Iceberg, because this form of acceleration where you're pushing down certain operations to a disaggregated storage layer is not dependent as such on any table format or file format. It's kind of agnostic. So for this optimization, so to say, to work, all you need is certain operations have to run closer to the data. It doesn't matter which format it is. And hence, this approach can accelerate access to open table format data. To give you an example, let's take a SQL query, select sum on a column, group by another column where customer country is equal to Germany. There is a syntax error in this particular SQL. Let me see who catches it, but that's not the point of this, this example. If you look at this query, the data reducing components in this query are the filtering, obviously, which is customer country is equal to Germany, depending on how selective this filter is. And also, this query is asking you for expression. It's neither asking you for rows nor columns. So it's actually doing a local sum. It's actually doing a sum, right? So we push down the filtered scan of local data and the sum itself to each local storage node, so to say, right? And what gets returned from the storage layer to the engine layer is an intermediate result rather than raw data. So in this particular case, if the filtering itself is like very, very selective, then you end up retrieving a lot smaller payload from the storage layer. So how do you decide what to push down and what not to push down, right? If you push down everything to the storage layer becomes a database, right? And if you don't push down anything, then it becomes a data lakehouse, essentially. So that decision, the thumb rule for that is like, if there's an operation that can reduce the data fetch and that does not take significant compute, and it can exploit data locality, right? Those are the operations that we push down. And how do we do it? We basically augment the optimizer in the SQL engine to actually take this call. So it's actually a coordination between both the engine, SQL engine layer, and the disaggregated storage layer. So it's not 100% disaggregated. There's, as I said, the pendulum just swings a little bit, but not too much to the side of tight integration. So that's how we decide what to push down and what not. So yeah, I mean the product itself bundles the SQL, ANSI SQL execution engine layer on top of the ES3 accelerator, and it is provided as a SQL analytics infrastructure. So some benchmarking that we have done, obviously, because we're talking about the performance here, especially the cost performance. So we took a sample workload of about 10 terabytes and workload volume of about 500 hours a month. Typical, mid-tier organizations needs, maybe to the smaller tune, because it's like, people sometimes talk here in these type of events in petabytes. So if you use an extra large instance from multiple cloud data warehouse providers, the t-shirt sizes have somewhat become uniform, if not exactly uniform these days. So you're looking at a 338K in annualized bill for this type of workload. S3 is, thank God, it's very, very cheap. It's $23 per terabyte per month. So you're looking at something like 341K. So in our case, what we do is we actually add a line item to the bill, which is ES3. And ES3 is more expensive than S3 because it has more compute packed per unit data. So it costs about $60 per terabyte per month. And it is implemented as a combination of EC2 instance and the EBS or local disk. And hence there is no access cost involved here to the data. And what it does is it brings down the compute consumption in our extra large so much so that it ends up costing 68K with 100% markup and 50% gross margin. I'm just talking about sample unit economics. That's not necessarily our go-to-market strategy, but we can reduce the TCO by pretty big margin. Even adding the 50% gross margin is what our claim is. And this testing was done with TPC H and also TPC DS up to 10 terabytes volume range, data volume range. So we've had some interesting deployment use cases. One of the early adopters was this company called as Gordian, which is a cancer drug discovery company. They have an interesting problem in the sense that they work on dark human genome, which is basically majority of the human genome that is not very well understood. And they think the cure for cancer lies in that portion of the genome. So they do pretty significant compute-heavy workload. And we were able to provide them with this value proposition, and they're actually using us in their actual analysis and research data. So I'll just, in the interest of time, I'll just say that it's time to reimagine the whole storage side of the equation, and of course, the compute side. There's a lot of innovation. There are way too many products out there that innovate compute very interesting ways. But I think it's probably time to look in the storage layer. That's basically the message from me. Thank you.
All right, tough questions. So thanks. It's a nice presentation. So you compared Databricks versus Akash X, right? So do you guys build your Spark engine, or it's an extension to Spark, or if you have to use Akash X, what is the way?
Yeah, our goal is to basically support multiple engines on top. Our core innovation, as I said, is on ES3 side of the things, and then the changes to the engines on top is basically to push down operations. So yes, in that case, yeah.
Okay.
We also plan to. We are still iterating on what engine to have as our default engine. We're trying out with DuckDB. We're trying out with Spark, of course, and other ANSYS SQL engines. We will hopefully be able to resolve pretty soon. Yeah.
Okay. So is this also available in Google Cloud? We are on Google Cloud.
You're on Google Cloud?
Yeah.
Yeah. So we the other approach that we're taking is we are purposely not taking a heavily multi-tenant architecture. So we are providing, we're choosing single tenant but elastic approach. So yes, we can deploy on any clouds.
Very good. Thank you very much. Thank you, Akash. Really, sorry, the Akash Cloud.
Akash X, yeah. Thanks.
So Akash, by the way, I mean, those of you who don't know, Akash is the sky and clouds are in the sky. So
yeah, the idea was that we want to elevate the standard of the cloud.
Yeah, raise the bar, of course. So really cool name. Thank you very much.
Thank you very much. Yeah.
All right. All right. Anton, you're up. Amazing session now. Databricks, take us home. Okay, I'm going to set you up. If you want to introduce yourself in the meantime.
Sure, it's surprisingly a lot of people for this time of the day. My name is Anton. I'm Iceberg PMC member and a software engineer at Databricks. Prior to joining Databricks, I used to lead all of the Lakehouse efforts at the data platform at Apple. So we've been working on Iceberg for quite some time. Yeah, and the topic of today's presentation is the evolution of position deletes in Iceberg. So where we started, how it evolved, why, and where we going next. Must be a long day. All right, thank you. So why should anyone care about position deletes and their evolution overall? And in my view, position deletes are a feature that goes far beyond providing like small incremental improvements to existing pipelines. It actually enables fundamentally new use cases. In Iceberg V1, if you ever did a merge operation and then you updated a record in every file of the table, you ended up rewriting the entire data set for each batch of changes. And of course, that wasn't sustainable at any reasonable scale. In Iceberg V2, we added the concept of position deletes to efficiently handle changes that are scattered across the entire data set, and they're very sparse in nature. They had minimal overhead on read, and they were relatively simple and easy to maintain. And we'll start by reviewing the original design, and we'll try to spot some of the inefficiencies. The V2 spec relied on position delete files that identified records that were removed by the file location and the row position was in that file. Those were regular Parquet or Avro files, was the file path and position columns in them. They could have different granularity. Originally, we started with partition scope deletes, meaning that a delete file can contain deletes for all of the data files within a partition. But then we quickly realized that not knowing at planning time which data files a particular delete file applies to causes a lot of issues. You have false positive assignment of deletes, you have extra overhead on reads, you also have issues maintaining them. And that's why we added file scope deletes. File scope deletes, on the other hand, can only contain records for a single data file. And that's more refined design, allowed us to do a lot more optimization, and that's the default in Iceberg 1.8 that's upcoming for all of the V2 tables. Here are some examples. So suppose you have 2 data files and you need to remove 3 records out of it, out of them. If you're working with partition scope deletes, then you can put all of the 3 records in a single delete file. If you're working with file scope position deletes, you have to separate them out. So yes, you're producing more files, more physical files on disk, but they are more targeted. So the Iceberg metadata would tell us exactly to which data file a particular delete file applies to. Iceberg planning is done in 2 phases. First, you build a delete file index, and then you stream through that delete file index, and you assign applicable delete files to the data entries. File scope deletes are assigned by partition, which means that you can have false positives. Imagine you have a partition with 10 data files in a single delete file. That single delete file may contain records for only 2 of the 10 data files, but Iceberg doesn't really know that. So once the planning happens, that single delete file would be assigned to each of the 10 data files, and then you would have extra overhead on read. With file scope deletes, we track the reference data file location. So the assignment boils down to a lookup in the map where the key is the data file location and the value is a set of deletes that are assigned. Reads are fairly efficient. Engines read the data as if there were no deletes. They materialize their columnar batch, fully vectorize that, no change. The only overhead is the need to build a deletion vector in memory. In most of the engines, it's a roaring bitmap, and that roaring bitmap essentially hides particular records from the downstream operators. So it's a very minimal impact on the read performance as long as you properly maintain those position deletes. Writes also depend on rowing bitmaps because the positions that are being removed come in different order and the spec requires them to be sorted in files. You have to first buffer them. And this is what most of the writers use. They buffer them in rowing bitmaps. And once the task is done and the writer is closed, you explode the bitmap in sorted order, and then you flush that state into Parquet, org, or Avro file. The spec in V2 was very flexible in the sense that it did not require any synchronous maintenance, and the engines could just defer that indefinitely. The library comes with all of the built-in actions for minor major compaction, expiry, cleanup, but those have to be triggered manually on demand or through a table management service. So while the V2 tables have been deployed like widely, and some of them contains tens of petabytes of data, there were some things that we wish we could do differently. In particular, we don't want users to choose between fewer files on disk and the ability to precisely assign deletes, right? You want to have both of those. You also want to reduce the reliance on the external maintenance. You want to defer that as much as possible, and you want your writes be efficient, yet still do some of the work for future reads. And also, we wanted to get rid of the overhead in readers and writers, because the on-disk and in-memory representations are different. In memory, you're working with a bitmap. On disk, you have to explode into key value pairs. You have to basically write into a Parquet or Hover file. So Iceberg v3 essentially gives us an opportunity to rethink some of that. The v3 spec adds deletion vectors inspired by Delta Lake, which identify records that are removed within a file by position in a bitmap. So Iceberg from day one used rowing bitmaps in readers and writers. But now in v3, it would be also possible to persist those as binary blobs in Puffin files. We also changed in the requirement to have at most one deletion vector for a data file in a snapshot, which would force engines to at least do some maintenance during writes. Here's an example of the blob layout. So there are multiple sections in it. First, you have the length field, which tells you the number of bytes that it's a sum of the magic bytes and the rowing bitmap together. The magic bytes is there for sanity check. Once you're reading the blob, you want to make sure that prior to deserializing the bitmap, you deserialize what you expect, right? So that's just basically like a sanity check. Then you have the rowing bitmap itself. It's persisted using the portable serialization format. This is as close as you can get to a spec for 64-bit rowing bitmaps. And then at the end, you have checksum. Checksum is there for data integrity. So if for some reason you cannot deserialize your bitmap back, you want to know if it's a problem with the serialization mechanism or if it's a faulty storage that gives you bit flips. So the checksum is kind of to address that. These deletion vector blobs actually persisted in Puffin files. So the Puffin file is a file format that's part of the Iceberg spec that was added for table statistics. And the primary goal is being able to store and retrieve binary blobs efficiently. It's something that is not possible either with Parquet or with Avro. And different deletion vectors are persisted in one Puffin file. What's important is the blobs may belong to different partitions as well. So previously, like if you had a table with 1 million partitions, at the very minimum, and you modified all of them, at the very minimum, you would produce 1 million delete files because there would be at least one delete file per partition. And those were really teeny tiny. With this design, we're no longer bound to partition boundaries. We can actually coalesce beyond that. So basically, you can put blobs that belong to arbitrary partitions in a single file. Puffin files are self-descriptive. You also have a footer For DVs, we persist the offset of each blob, the length, the type of it, and the reference data file and the cardinality. So if you just have access to this puffin file, you would still be able to make sense of it. At the same time, we're not using the footer during reads because of how the metadata tracks these blobs. While they are persisted in a single file, each blob is being tracked separately in the metadata. So you would have separate metadata entries for each deletion vector, even though they're part of the same file. So how we do that? We did add more fields that help us achieve that. In particular, we added the content offset and the content size. So basically, this is an example where you have a puffin file with 2 DV blobs in it. And at the top, you have 2 metadata, 2 delete manifest entries. The content of them is position deletes for both. File format is puffin. The file path is the same, which is the path of the puffin file that it comes from. But the content offset and the content size are different. So the content offset is where you need to jump within that file and where your blob would start. And then the content size is how many bytes you have to read to fully fetch the blob. So whenever you're reading, you actually don't have to touch the footer. Footer is there for debuggability purposes, but it's not necessarily to send an extra request because it's a puffin file. So you can actually jump directly to an offset and consume the entire blob. We also added the reference data file field. Previously, the way we reconstructed it for file scope deletes from bounds. So essentially, you had some overhead with that because you worked with byte buffers and then you had to convert those byte buffers to a string. You need to compare that the string is the same, and then you could use it as a reference data file location. It's no longer needed, and that was at the critical planning pass before. So if you're like working with a table where you have 10 million of delete files, it adds up. So it is a substantial improvement that you just persist the reference data file location, and you can use it directly. There are also some behavior changes, like I said before. There can be only 1 DV per data file in a snapshot. So engines would have to combine them once they add new deletes or new updates. So all in all, the V3 spec allows you to track deletes per data file, but do not require you to produce teeny tiny files on disk. So you kind of get the both worlds, the best of both worlds of the partition and the file scope deletes, or even actually better, because you're no longer bound by the partition boundaries. You get faster reads and writes because there is no more overhead. You have roving bitmaps in memory and you have them on disk. And hopefully the synchronous maintenance that now would be part of the DML operations would also defer the need for that manual maintenance and would keep the performance more stable. The spec changes are fully done. Core implementations would be shipped in 1.8. You also have full read and write support in Spark 3.5. Major compaction is done. Expiry is there. You can remove orphan files. So basically, it's like you can get end-to-end working experience for them. What's missing is the automatic conflict resolution. So that would be done within the library as well. So the library would be able to detect the conflicting DVs and would be able to combine them for you. We're also working in some minor compaction. So for instance, if you have a DV file where only one of the blobs is still live, you want to be able to expire that file. And for that, you need to move the live DVs into another DV file. So that would be shipped later. There's some remaining work with partition stats. We have to update that. And there is some ongoing work how to maintain the deletes synchronously in Spark. We do this through a broadcast right now, but there are more intelligent ways to do that. That's about it. Thank you.
I know deletes are the toughest ones. We always work with.
Hi, Anton. Thanks for the talk. Curious on the in-memory representation part. The way you explained it makes it seem like it's obvious to have the in-memory representation be the same on disk and in memory when you're doing the V3 approach.
Yeah.
I'm curious as to why in V1 and V2 that approach was not taken and why you chose to do the parquet approach instead.
Yeah, part of it is that there are a number of questions that we didn't know, we didn't have time to answer. So basically, one of them was, what's the correct serialization spec that you can use for roaring bitmaps? The roaring bitmap itself has a very clear standard how it should be serialized if you're working with 32-bit numbers. In case of Iceberg, we were using the 64-bit version of the library, and the library itself was not the bitmap that we were using was not actually serializable, and there was no standard. So we were kind of reluctant to a little bit explore how to do that serialization. We didn't want to come up with something extremely custom. That was the first point. The second point was we were not sure, because the roaring bitmap may not be the most compressed representation of an arbitrary sequence of integers. So we were worried about the size on disk, right? And we only did all of that evaluation at a later point in time because we focused on the rest of the ecosystem. So basically, we knew we wanted to get there at some point, soon after we kind of started productionizing those use cases, especially when we pivoted towards file scope deletes. Because the file scope deletes is where you get the ability, hey, I separate all of my deletes in a particular delete file, and I know where it belongs to. So this is where it's solidified, that idea that you need the targeted deletes, basically. And then after that, it was just a set of open questions that we did not explore. Some of those questions were already answered by the Delta Lake community, right? So for instance, Delta Lake uses the same blob layout, which we kind of inspired by. And they also use the portable serialization format. Because it's both projects, so it's kind of a standard now, I would say. No, you can still have like many manifests. So like each manifest entry would be dedicated to a particular DV blob, deletion vector, and it's represented as a delete file anyway. In the Java API, it's also represented as a delete file like prior to that.
Thanks. What's the best way to basically move to the rough and delete files at this point? So the V3 is not there yet, and the 3.5 Spark is not so widely adopted. Is it possible to somehow get all those advantages at this point?
So V3 is actually like a lot of the parts of it are fairly done. What's not there is like we didn't close it, so we didn't vote on it. Like I think Dan was mentioning earlier about some of the things that are not there. But DVs are like fairly more or less tested, I would say. So we are fairly confident in the design. And I think we backported some of the changes to Spark 3.4, but you'll have to use Iceberg 1.8. That's the first release that has some bits of the V3 spec. The migration path would be fairly easy, at least in Spark. So once you bump the format version, the first merge operation would actually take care of that. So once you bump the version, you no longer can add old style deletes. They can still be there if they were before, but you can no longer add new old style position delete files. You can only add DVs. And the spec requires that DV that are being added, they actually have to include all of the historic deletes that were there before. And this is what the Spark implementation is doing. So whenever you do the first, let's say, merge operation after the bump, it will seamlessly produce a DV for you and drop the previous delete files that existed. So it's a seamless migration. that happens once you start using the V3
I
Spark.
see. So basically, if I have 3.4 Spark, the only thing I need to do is make sure it works with the Iceberg 1.8, and I'm just altering my tables for the V3 and making sure all the reads and writes are happening with the 3.4 and 1.8.
Yeah, I mean, like you won't be able to. Yeah, exactly. So you won't be able to, once you do the upgrade to V3, you won't be able to kind of write into this table from an older client, if that makes sense.
That's, in my case, write is the sort of a single source of writes, right? Multiple reads, but single source of writes. So in this case, it's super
But
simple.
we really thought about the migration story. We didn't want people, hey, like in order for you to migrate to V3, you actually need to run something and do the full migration. I mean, you can choose to, like there would be the action to rewrite all of the old style position deletes on demand if you want to, but it's not required. So the old style deletes are still valid. You just can no longer add new ones.
I see. Yeah, I see a lot of benefits in that. Any estimations where, so basically we're running partially Spot.io, partially EMR. So I'm just like with a Spot.io, I can put everything like the Spark 3, even Spark 3.5, 1.8, whatever. Any estimations when the Amazon gonna catch up to that?
It's a good question. We hope the community adopts. I think there's a lot of push from customers. So
I have a new role. I'm a wedding planner.
But we're kind of doing whatever is possible to simplify that migration for other engines. So a lot of this is part of core. So we are thinking about, like we chatted with Trino folks, we chatted with like whatever engines we're interested with Snowflake as well. It's a cross-engine effort, and we made sure that the design actually aligns with everybody and it's easy to adopt. So it's, and again, like it will take time, but because the in-memory representation is exactly the same, I don't imagine this to be far in the future, I would say.
Thank you. You know, if there wasn't any pain in life, what fun is there? Right. All right. Hey, all right.
So is a conscious design choice here to like move more work to the writer versus deferring it? Like typically Iceberg is like the deferred maintenance work, and it's conscious choice to like do that in line here. And I understand, like, but just like, give me your sense of like the trade-offs you see in that decision here, like why now is the time to do that? And then do you see other opportunities in Iceberg generally where that might also make sense?
Yeah, we've been burned by the V2 pass because we were very flexible and we thought that, hey, the engines would do a smart thing. And what ended up happening is that they just, because of the spec was very flexible and you didn't have to do any maintenance during writes, nobody did that at all until the performance degraded so much that folks started to complain. Hey, and of course it was so easy. You just kept adding it until like you couldn't read it anymore. So basically that was the lesson that we learned, that sometimes that flexibility is a bad sign. Not everybody has the table management service in the background. Nobody maybe understand how what's the maintenance that's required and so on. We were very careful with the overhead that we adding, and we did like a lot of benchmarking to see that this maintenance that happens, at least in Spark, it's in a distributed fashion. So it's not done on the driver, it's actually part of the job. So it's done on executors in a distributed fashion. And based on the benchmarks that we've done, like you wouldn't even notice that. And this is anyway the work that you were previously doing during reads, because during reads you had to read all of the historic deletes and you had to combine them into a single bitmap. So you already were doing that work on reads, so it just makes sense to do it on the write and then simplify it.
Very cool. Right. Really, thank you, Anton.
Thank
This
you.
is a
Thank you,
really,
everybody.
Really good talk. Okay. with that, folks, I really want to thank each one of you from the bottom of my heart for sticking for so long, first of all. You were literally holding the fort. But if I start naming names, it's going to take forever. So let me just compartmentalize speakers. You put a lot of effort into getting the content in there. Clarity takes a lot of time. You raise the bar. The community, without which we would not have been where we are today. And it's really about us, meeting and breaking down these barriers to really understand what actually can be done and what's optimal to make the things move. Today, when we go into real world problems, they are mainly because of the way we've designed systems for the last 30, 40 years. And they become isolated because that's how the systems work. But today we have the ability to think beyond that point. And I think the community is really what's going to help drive that transformation in the industry. So let's do more of these. I really, really appreciate everybody, Puppygraph, Databricks, a big shout out to you guys. And Daniel and Jason, I think having you here was phenomenal. I think we learned so much, and how deep you have been thinking about this is not just, evident in the product, but it's evident in your conversations. So really appreciate you being here. Now, we have been asked by security that maybe 8 o'clock is probably the limit we can be here. So no rush, but we have like 20 bottles of wine, and we have about 40 cans of beer. I would like to see who can drink those as fast as possible and be able to drive back home. But, big thank you. Thank you very much.
Thanks for watching.